All right, so then let's actually get started on the counterfactual learning and evaluations tutorial for recommender systems. My name is Thorsten Joachims. I'm faculty at Cornell University, and
hi everyone, I'm Yuta Saito. I'm a first-year PhD student at Cornell University working with Thorsten.
So what we're going to do over the next 3 hours, plus coffee break, is the following. We'll introduce you to this kind of growing area that intersects RecSys, information retrieval, machine learning, reinforcement learning in particular, and talk about two main problems. And since it goes through different communities, these problems have different names, but they're actually the same thing. How do we evaluate these systems? And often it's called counterfactual evaluation, offline A/B testing, off-policy evaluation, or what we'll use for short here is OPE. That's the shortest abbreviation we could find. And then how do we, once we know how to evaluate a system, how do we learn these systems? And counterfactual learning, unbiased learning to rank, off-policy learning, or OPL are the kind of common terms that people use for this. So coming out of this, you should be familiar with the fundamental concepts and the basic methods. It's a very active field, so there are lots of recent advances and that really are very practical in their orientation. We'll also kind of give you tools for getting started and doing hands-on work on this, and say a little bit about what's the remaining research problems, and there's quite a set of interesting problems.
And also, there's a tutorial website and all the slides, and there's a GitHub repository, so you can access all the resources of the tutorial. So yeah, let's visit the tutorial website. I think some of you cannot see the screen clearly, so you can just visit the website and you can get a slide. And so this is a tutorial schedule of the whole session. So the Thorsten is going to start off. He's going to talk about the problem setup, the motivation, and foundation of policy evaluation, or in general, offline evaluation in recommended systems. And then we're going to take over, and I am going to talk about advances, recent advances in OffPolicy estimators. There are lots of exciting, recent advances there. And also after that, I am going to talk about what's going to be the issue, what's going to be the challenging problem when we apply OffPolicy evaluation to a more practical setting, possibly relevant to recommend the system or ranking system. And we're going to take a maybe 20 minutes, 30 minutes coffee break. And there's a second half, which is a bit shorter second half. And Thorsten is going to talk about OffPolicy learning, how to learn a new policy, well-performing policy using only log-bounded feedback data. That's the topic here. And right after that, I'm going to talk about more of a practical stuff, implementation, how to implement OffPolicy evaluation, OffPolicy learning in an efficient, easy manner. There's a great package there. And right after that, there's a final section. We're going to just summarize the whole tutorial and take some question and answers. That's basically our plan. Sure.
Cool. All right. So I'll start out with kind of setting the stage and talking about the two main approaches that exist for the evaluation problem. And at the core of all of this is kind of a view of recommender systems, not as making predictions, but really about systems that are acting, that are making interventions in the world, and that are making interventions to have a desired effect. And that changes your mindset to a more causal kind of problem, and the techniques that we need for recommender systems are also going to be drawn heavily kind of on causal methodology. So, and I think this applies not just to recommender systems, it applies to lots of other problems where we use artificial intelligence or machine learning these days, all the way to autonomous driving, for example. It's really about making interventions in the world to have a desired effect. So let me give you a concrete example of what this looks like for a recommender system. And that's a kind of example that we'll use throughout this presentation. You have a user coming to your system. Your system then takes an action. For example, it recommends these 3 products personalized to this user. And this action has a desired effect, and that we measure in terms of our reward that we get. So the reward in this setting could be, for example, that the user clicks on something or even purchases one of these items. And what we want to optimize is this downstream effect. It's the rewards. So the problem is reward maximization. It's not predicting click-through rates. Predicting click-through rates can be helpful in reward maximization, but it's not the ultimate goal. So make this a bit more abstract. I think a lot of kind of recommender systems problems can fit into the following kind of theoretical setup. You have a kind of a context coming in, a user, a query, a description of that user, and that we call the context, and it's typically described by X. That's our input. Then we have a policy, that's our system, policy pi, that selection action. So for example, recommending a particular set of products. And then we observe the reward, maybe clicks or revenue or purchases that comes from this action. That's what we typically denote by R. And every interaction with the system we think about as one of these contextual bandit, that's what this setup is called, contextual bandit interactions. Context comes in, policy takes an action, we observe a reward. That's a simplification. We'll talk a little bit more kind of in the end about extensions of this, but I think it's a very useful abstraction for many recommender system problems. So let me give you a couple of examples. So for example, here Netflix, we want to recommend what to put in this banner up here. So we need to pick a single movie or a single show to put up there. In comes the context, that's maybe my user profile. The action is which movie to put up there, and the reward is whether the user engages with it through a click or even watches the show to the end. And we want to maximize the reward as a proxy to user satisfaction. Second example, maybe let's take YouTube. So we are currently on this page, or on this video, it's about off-policy evaluation. And so that's our context X. The action that we can take is to put a ranking of other videos here. And we want to maximize here maybe the click or the downstream dwell time. And that's our reward. And then the final example is, again, this fashion example. We have a user coming in with a particular query and maybe also some description of the user. We can put 3 items here. So we have a combinatorial kind of action space. And the reward is whether the user engages with these items or purchases one of those. So all of these fit quite nicely in this contextual bandit setup. And there's many more. News recommendation, a slate of news articles that you want to have on some personalized newspaper front page. Music recommendation, like you would have at Spotify. Personalized artwork, so actually which artwork is shown in the banner is also personalized to kind of highlight what the user particularly may be interested in the show, or ads in general. I mean, it also goes far beyond this, right? The general setup is also something that applies well beyond recommender systems. So there are 2 main problems that we have in this space. The first one is we have a policy, so some system that takes action, and we want to evaluate how good it is. What's the average reward that it gives us? And that's the policy evaluation problem. And once we know how to evaluate policies, we can also do learning, right? Then we can say, okay, find me the policy that maximizes reward from this particular space of policies. And we'll talk about both. The first half of the tutorial is about policy evaluation, and then the second half, after the break, that's going to be about learning. Okay, I've used this word policy a million times already. Let me actually define what that is. So a policy, we'll look at 2 different types of policy, deterministic and stochastic policies. Deterministic policies basically are just a function, pi, that takes in a context X and spits out an action A. This is what we should do. This is the action that we should take. And the visualization that I'm going to be using is this one here. This kind of visualizes kind of the square is all the possible action the system could take for this context. The shading says, oh, these are good actions, green, high reward, bad actions, red, low reward, and any particular point in the space is a particular action to take. So for example, policy pi 1 takes this action up there, not that great, right? Policy pi 2 takes a more greenish action, good action, right? Higher reward. We'll often actually use stochastic policies, and there's going to be good reasons that are going to be obvious at the end of the tutorial. And a stochastic policy is just a generalization of this, where we say our policy is a probability distribution. It picks not one particular action deterministically, but it picks actions kind of stochastically according to a distribution. So here pi 1 picks from this distribution of actions. Here this one picks from this kind of more greenish actions, the better actions. So, and of course, the deterministic policy is just a special case of a stochastic policy. You just put all the probability mass on one action. So let me formalize this contextual bandit setup a little bit more. What we have is these vectors coming in, these context vectors coming in. They come from a distribution P of X. We just draw them IID, just like in supervised learning, right? The X's come in IID. Our policy, which is now stochastic, or the special case of deterministic, then conditioned on the X picks an action from the probability distribution pi. And then our rewards are stochastic as well. Given a context and an action, there's a certain distribution of rewards, and we sample a reward from it. You know, clicks are not deterministic, right? If we go through this, the type of data that we collect is log data. So we'll call this D, and it's typically these triples of context that came in, action that we took, reward that we observed. And now we typically get lots of this type of data, right? That we just get from normal system operation, basically. Log data we have plentiful. And this log data is just coming from a product distribution. So, you know, each of these tuples here is just coming from kind of IID drawn from context, action, and reward. And of course, this distribution we don't know, but we sample from it naturally. Our users come in, right? This distribution we also don't know. Our users giving us reward, but we can observe what users do. This thing we control, right? That's the action, that's our system that we've built. We control this. This is our policy. So what are we typically interested in? Well, we can be interested in lots of things, but for the purposes of this tutorial, let's say we're only interested in the value of a policy, that is expected reward. I'll probably not have the time really to talk about that. You can also estimate other quantities using exactly the same techniques that we have here, like fairness type of quantities, or other constraints that you may have on your policy. But it basically comes down to the same thing. So the value of a policy is the expected reward of running this policy. So it's this big integral there, but it's really just very simple. It's the expectation, right? It's the expectation of users coming in, taking actions according to our policy, and seeing the reward. And so, like for this context, our policy picks this, kind of reddish actions probabilistically. For some other context, this, right? And we're just taking this big average, and what's the average color, so to speak. That's what the value of a policy is. And typically, we want to maximize this. Sometimes, some place in the talk we'll switch to minimizing it, but it's the same thing, right? We want to optimize this quantity. So what's the simplest way of actually estimating the value of a policy? That's the policy evaluation problem. And the simplest way to do this is to put this policy into production, right? To put it into our system. And we call this an A/B test, especially if we have multiple policies that we want to compare. We just, implement this policy, put it in front of users, and then, we have the users interact with this policy. We call this pi E for evaluation policy. We get data from this policy, and then estimating the value is super simple, right? We just take the average rewards that you observe, and that's an estimate of our expectation. So I think that's the gold standard in evaluating policies. Everybody does that. Now, but what's the issue with this? It's good thing about it. It's conceptually quite straightforward, right? We just build it, we field it, and we see how well it works. From a statistical perspective, it's unbiased, right? It's not, if we field the policy, we get an unbiased estimate. In expectation, we get the right estimate. It's consistent in a sense that if we get more and more data, if we run the policy for longer and longer and longer, and our user distribution doesn't change, eventually we get spot on the right answer, right? We get converted, we go law of large numbers. And there's really few assumptions compared to the other things that we'll talk about later here. It's very robust. But there's definitely a number of cons as well. First is, if our policy pi e that we want to evaluate, that's a new policy, we don't know how well it works. If it's a bad policy, we put this in front of our users and customers, and that has a cost, right? If it's a bad policy, we're fielding it, that's not good. It's also a lot of work, right? We have to actually productionize this policy. And that can be quite a lot of work, right? It has to be robust, it has to fulfill the latency requirements, everything. That takes weeks of work. And then you have weeks of potentially fielding this policy and gathering new data. So the turnaround times that you have are really on the order of weeks or even months for trying out a new policy and getting its value. And so there's no way you can do this for hundreds or thousands of policies. You don't have enough traffic, you don't have enough time to do that. So this kind of online, on-policy A/B testing that we have here, doing this kind of for each policy, fielding each policy, it doesn't scale. What we would really love to do is the following. We would get data from some historic policy pi null, and that's our logging policy. We collect this data. It's maybe the data that we collected last month. And then, without fielding any of the new policies that we want to evaluate, we want to have some method, some estimator that would tell us how good these methods are, but only using the data that we collected from this policy pi null, the data that we already have. And potentially, that lets us be much, much faster, right? So what we need is what's called an OffPolicy Estimator. So we want to evaluate the policy, the value of policy pi e. That's our evaluation policy. We don't know how good it is. And what we want is an OffPolicy Estimator v hat that takes in that policy, that new policy that we've never fielded, and data from this other policy, pi null, and spits out the correct value of that new policy pi e. And the way we'll think about it is answering this counterfactual question. Basically what this estimator does is it answers, how would pi e have performed if I had used it instead of the policy pi null that was actually running on the system? So it's this counterfactual question. How well would pi e have done if I had used it in terms of pi null? That's why it's often called counterfactual evaluation, because you're kind of trying to turn back time and see how well you would have done if you had used a different policy. So what we're doing here is we're actually estimating online performance, exactly the online metric that you're typically trying to optimize, of a new policy that you've never fielded before without doing an A/B test. So there's, often you have this online-offline gap, right, where you're optimizing something offline, and that's like a proxy for something that you want to optimize online. That's gone, right? We're using exactly the same metrics, and we're optimizing exactly the same metrics. So what are the pros and cons of this? Pro is We don't have to collect new data. We can potentially do this for as many new policies that we want to evaluate as we want. We're never fielding PI-E, this new policy, so there's no potential for harm to the customers, right? Even if it's a bad policy. And quite, often many policies that we try are actually quite bad. Any cost from collecting this data PI null actually gets amortized, right? We collect this data once, and then we use it over and over and over and over again to evaluate lots of new policies. So even if there was some harm or some cost to collecting data from PI null, it actually gets amortized over many kind of offline A/B tests. We don't need to productionize PI-E, right? So all of this additional work goes away, and that means fast turnaround times. We can evaluate a new policy in seconds, not weeks or months. The cons is it's actually a harder problem, right? And we'll have to make more assumptions to be able to do that. But it's also, there's rapid progress in actually making this possible. And we'll talk about what this progress is in this tutorial. And then once we can evaluate, then we can also do off-policy learning. So we can use our evaluator to find the policy offline that maximizes online performance, and that's basically learning. So we basically do offline learning of a new policy that optimizes online performance, and we can use the same supervised learning workflows that we are used to, instead of having to do some kind of online learning instead. So what we will get, hopefully, at the end, is some kind of workflow that looks like that. We collect our log data, the data from last month operations of the system. That's our D null. We split it in train and validation or some other cross-validation scheme. We train on the training data, come up with some policy pi hat. We do cross-validation for it, see how good it is. That's where we use the validation data for, estimate online performance. If we're not happy with it, we keep tweaking the hyperparameters until we are satisfied with what we have. Then we have an estimate of how well this works. Does it actually work better than the policy that's currently in production? And that accurate, if this estimate, if we did everything right, it's going to be accurate. It's going to tell us exactly we're going to gain 100 bips. So that eventual A/B test that you're maybe running as a sanity check should be completely boring. If you have done everything right, you should get exactly the same number out of this that you already have. But you still probably want to do this just as a sanity check that there are no bugs. So that's the general vision and workflow. Okay, but everything hinges now that we can actually do this off-policy evaluation, that we can use data from a different policy to evaluate a new policy PI-E. And the quality of an estimator is typically, or will use the mean squared error to characterize the quality. That means if this is the true value that we don't know, the mean squared error is like the squared deviation of our estimate from the truth. And so, like for every estimator where we have squared error, we have a bias variance decomposition, and we have to think about both the bias of the estimator and the variance of the estimator. And that's going to come up throughout the whole tutorial. So let me give you, there's two broad classes, two approaches to solving this off-policy evaluation problem. There's the model-based approach and the model-free approach. And let me give you the intuition of both of these. And then we'll see lots of variations on the theme, but the basic ones are the following two. So to understand these two, let me do a very quick introduction to the potential outcomes model as one of the kind of foundational ways of looking at causal inference problems. And let's do it not for our domain, let's do it for a medical problem. Let's say our problem is that we want to have a policy for treating heart attacks. And so there are three different treatments. There is, you can either do bypass surgery, you can put in a stent, or you can put in drugs. And I don't know anything of medicine, so don't take any of this with any realism. So we have three possible treatments, three possible actions that we can take. And now we run a controlled randomized trial with 11 patients. And the first patient got the bypass surgery. And the outcome is unfortunately bad. So RI is the 5-year survival, 0 or 1. X2, the patient number 2, got the stent, positive outcome. X3 got the drugs, also a positive outcome, and so on, right? That's our data that we have. So, but of course, you see that this is very much the same as the problems that we have, right? So for example, if we have the problem of placing a vertical on the SERP here, then maybe you have 3 different actions that we can take. We can either put it in this position 1, between these two, position 2, between these two results, or position 3 down here. Let's see, these are our 3 actions, not stent, bypass, and drugs, but position 1, position 2, position 3. There's a chosen treatment for any user that comes in. And then we see our outcome, our reward, whether users actually engage anywhere on the SERP. That's our reward. Structurally, it's exactly the same. So what's the issue here? What makes this complicated, dealing with this data? Well, there's the factual outcome, and the factual outcome is the action that we actually took for this patient or for this user. And we observe the reward for that action. So for this patient 6, or no, user 6, we put it in position 1, the user interacted with the SERP. But we don't actually know the counterfactual outcomes. You know, what would have happened if we had put it in position 2 or in position 3? What would have been the reward in these cases? So we're dealing with missing data here, right? We only observe the outcomes for the actions that we actually took. That's what log data is like. And now you probably see why doing this counterfactual evaluation is hard, or evaluating a different policy. What are we going to do if our logging policy that collected the data picked this action, but our new policy that we want to evaluate picks one of the counterfactual actions? We don't know what the reward is. What are we going to do about this? So there are 2 approaches. The first one is the model-based approach. And it's probably what you're thinking now, even if you haven't thought about this problem before. Well, let's just impute the other values, right? We know machine learning, so let's try and predict what the other outcomes would have been. So in particular, we'll impute the expected reward here. So we're marginalizing out the randomness of that reward distribution. But I've still used just 0 and 1s here, just otherwise the table gets too messy. So we'll just have some way of imputing all of the values in this table. And now if you want to evaluate a new policy, super easy, right? We know all of the values, and we can just compute it, no? So whatever that policy pi e takes as an action, we know the reward. We just compute this expectation, and that's our utility, or the value of the policy. How are we going to do this imputation? Well, we have training data, right? The black numbers here, they tell us what the reward is. So we can treat this as a regression problem. So we can use any of our favorite regression methods that we want. So we will find a regressor R that takes the observed values of the rewards. And now, based on the context and the action, we kind of come up with a feature vector that combines these two in an interesting way. It's a supervised learning problem, right? It's a regression problem. So that's one approach. But it often doesn't work that well. And let me give you some intuition for why it doesn't. First of all, the data that we have and the data that we predict, they don't come from the same distribution, right? It's actually a distribution or a covariate shift between the two. And what happens is the following. So let's say we've come up with a regression model that has 2 features, this feature and this feature. The green and the red dots are the observed points. And now we learn a regression model. And what could be happening is that there's actually vast regions of the space where we don't really have any observations. But our new policy may be in these vast regions of the space where we don't have any observations. So it really matters how our policy extrapolates, how our regression model extrapolates, right? And if it takes a curve like this or a curve like that, right? So it's very sensitive to these kinds of issues. What this means is that if our model is not right in extrapolating, then we get a biased estimate. It can be too high or too low for our policy. So can we avoid this bias? And bias is always hard to detect in a statistical sense. So that's where model-free approaches come into play. So what do model-free approaches do? They don't actually try to predict what the rewards are everywhere. So they only use the observed rewards. So this is now, let's say, for this particular context, we've picked actions A here, sorry about the typo. We know for these dots what the respective outcomes are, what the rewards are. Some red, some green. And this is the distribution of actions taken from our logging policy. And now we have a new policy, pi, that we want to evaluate that takes actions from here. What these model-free, and this in particular the inverse propensity score estimator does, is it reweights the observations by using these importance weights. So it takes the probability under the new policy that we want to evaluate and divide by the probability of the old policy that generated the data. And that's the weight that it puts in front of the reward. If these two are the same, right, if we're evaluating pi null with data that come from pi null, this will be just 1, and we have our online A/B test back, right? That's the standard estimator. But if they're different, if they have different probabilities of picking that action, then this importance weight is going to kind of adjust how we weight the rewards. So why does this make sense? Let me give you an example here. So that's the same reward data that we've observed, and lots of missing values here, lots of rewards that we don't know. So, but we do know the top left reward for user 1. And we know that under the policy that collected the data, pi null, picking that action had probability 0.3. Under the new policy that we want to evaluate, that probability is 0.6. So it's twice as high. So what does it mean? It means that in our log data, we would like to have kind of twice as often observed that particular action under the new policy as we did under the old policy that logged the data. And so what does this inverse propensity score importance weighted estimator do? Every time we see these observations, we upweight it by a factor of 2, right? Because that probability is by a factor of 2 larger than that one. So by upweighting it by a factor of 2, we're kind of getting it right in expectation. And let's look at the second row here. The old policy picked it with probability 0.4. The new policy picks this action only with probability 0.2. That means it's the other way around. This one picks it twice as much too often. So to correct it to our new policy, we just divide the weight for each observation by a factor of 2, which in expectation is again the right thing to do. So by doing this importance weighting, we're kind of adjusting for the over or undersampling by the logging policy and adjusting it to the policy that we want to evaluate. And the outcome is that we get an estimator that is unbiased. You know, these weights kind of cancel out the mismatch in distribution. One thing that's important, though, is that this only works if for any action for which the evaluation probability policy has a probability of greater than 0, the logging policy also has to have a probability of greater than 0, right? There has to be some probability that the logging policy took this action. Otherwise, we just have blind spots. But if this condition, is called the full support condition, is fulfilled, then this inverse propensity score estimator, IPS estimator, is unbiased. In expectation, is doing the right thing, just like an online A/B test is unbiased. And just like an online A/B test, if we throw more and more log data from pi null at it, we get more and more accurate. So we get consistency, we get convergence to the right number. The conversions can be slower because we have larger variance. But in principle, if our estimate is not accurate enough, if we have more log data, it will become more accurate. But there still can be variance issues. And that's much of what we're dealing with. So this is just the proof that it's unbiased. You can go through it if you have ample time. We're not doing it here. So what does it mean? So we have these two approaches. We have the model-based approach, and it's often called the direct method, DM. And we have the model-free approach. It's the IPS method, or inverse propensity score weighting method. And here's a kind of synthetic example, or a synthetic data set, where we have the mean squared error of the estimator, how accurate it is, on the log scale here. So lower is better. And here's the number, here's the size of D null, the amount of log data that we have. The typical behavior is actually, this shows typical behavior that you also see for other problems. For the model-based direct method here, where you're imputing the rewards, you are biased, which means that if you add more and more data, eventually your mean squared error, the estimator doesn't get any more accurate. For the IPS method, if you add more data, it becomes more and more accurate, just like an A/B test becomes more and more accurate if you run it longer and longer. But in the beginning, if you have little data, the variance of your estimator can be large, right? We know that this is unbiased, so any error in the IPS estimate must be due to variance. So that also tells you a little bit that there are trade-offs between the two. And much of what Yuta is going to talk about in the second part of the talk is how can you deal with these two extremes, high bias in the direct method and high variance in the IPS method, and kind of combine the two so that you get the best of both worlds. So with that, I'll ask Yuta to come on stage.
Okay, thank you, Thorsten. Oops, I still part one slide. Okay, we'll go back to the first one. That's right. Still part one. Okay, work. Oh, cool. Sure. So I'm gonna take over here, and let's look at the more bias variance, advanced bias variance trade-off, control. So there are lots of interesting, exciting, and advanced off-policy evaluation in recent off-policy evaluation community. So let's look at that. So this part is gonna be 35 or 40 minutes. So let me wrap up the previous section. So there are two extreme estimators, direct method and IPS. So direct method using a reward predictor. So it has high bias depending on the bias of or the quality of the reward predictor, of course. But the good point is that it has low variance. And the other extreme is IPS. It is zero bias, unbiased. But the downside is that it has a high variance in some cases. So there's a notorious bias variance trade-off there. So the main motivation, our main motivation or the main motivation of the many researchers in the past decade is like, we want to do better, especially in terms of variance, right? While being unbiased and consistent. So consistency means that if we have infinite sample of data, we can know the true policy value if we're using a consistent estimator, right? So consistency or maybe unbiasedness is just the necessary condition to be a good off-policy estimator, right? So the main motivation or main strategy here is we want to reduce the variance of the IPS estimator because it is already unbiased and consistent. And there are two main approaches in reducing variance or to aiming for getting variance reduction from the IPS. And the one is let's do some modification to the IPS, the vanilla IPS. And the other approach is let's do the hybrid of the direct method and IPS. And then we should be able to do better than both. So let me introduce some estimators in those kind of direction first. So the first estimator I want to introduce here is the ClipIPS estimator, or the ClipIPS estimator just. I think it's a very popular estimator especially for practitioners because it is very easy to understand and implement. So what it does is just the clipping. So it just cut off for the clips the large importance weights by introducing a scalar value hyperparameter lambda. So lambda is going to be kind of 10, 100, or 1,000, a kind of a bit large scalar value. And here's the definition. So you see a little bit of the modification from the vanilla IPS, right? So the vanilla, the original IPS uses true importance weight, but the ClipIPS does do some the modification to the importance weight input. So it just upper bound the huge importance weight by a pre-given hyperparameter lambda. So let's see how it works. So let me now use a simple toy example, just having two samples. So here is a x1, x2, and pi now is a login policy, the action choice probabilities in the log data. And the motivation here is, we want to evaluate the performance of an evaluation policy or a new policy. This is an unseen policy. But we want to evaluate the performance of this policy using only the log data. That's the motivation of policy evaluation. And this is just the vanilla IPS, works. So vanilla IPS, the original IPS, just the weighted average of the reward observation, and the weight is importance weight. Importance weight is just pi e over pi now. This is just the ratio of the two policies. And then now, we have two samples, and we have these numbers. So the problem here is that the red parts, meaning that we have an importance weight of 0.8 over 0.01. This is just from these numerical toy examples. So this is the downside was a source of high variance, right? We could have very huge value in the importance weight. That's the problem of the the variance problem with the IPS estimator. And here's how ClipIPS estimator deal with this problem. So it's too simple. So here now the lambda is set to 10. So when we have this hyperparameter lambda, we just cut off, or we just use the hyperparameter lambda as a replacement of the huge importance weight. Now the importance weight is 80, so we should let's replace that huge value by a hyperparameter lambda. That's it. Okay, so this is how ClipIPS estimator works. It just avoids the huge importance weight. Is a kind of clipping technique. So we should get some variance reduction because we don't use huge importance weight, but the vanilla IPS does. So we can reduce the variance of the IPS. That's the trick here. But the downside is that this estimator no longer uses the true importance weight. It loses the unbiasedness and consistency. It is no longer, it is neither unbiased nor consistent. This means that the ClipIPS estimator, if we use ClipIPS estimator, even if we have infinite sample of data, we cannot know the true policy value. That's not so good, right? So there is the other estimator in the modified version of IPS, which is the self-normalized IPS estimator. But the name of the estimator is pretty long, so let me just call this estimator the SnipIPS estimator. And this is also a pretty simple estimator, but it is very powerful, I think. So what it does is just rescale the estimation result of the vanilla IPS. So there are essentially the two parts, the red parts and the blue parts, or just the numerator and the denominator. The numerator, the red part, is just the the original IPS. This is just the empirical weighted average of the reward observation, and the weight is importance weight. I mean the pi e over pi now. This is exactly the same, right? So the difference is just the denominator, the rescaling factor, right? So this blue part is just the empirical mean of importance weights. Again, importance weight is pi e over pi now. And we don't see any reward observations in the denominator, meaning that this is just the empirical mean of importance weights. So this is kind of rescaling factor. We have a bit of a simpler form because we can just cancel out the 1 over n notation here. So this is a little bit of a different interpretation on what this SnipIPS estimator is doing, right? So typically we use 1 over n when we take an empirical average of something, but SnipIPS estimator doesn't use 1 over n. It uses the 1 over sum of importance weights rather than 1 over n. That's I think another interpretation on what this estimator is doing. So let's see how it works. So again, the same example, having just the 2 log magnific data. And the problem of the vanilla, the original IPS, is that we could have a huge importance weight, the 0.8 over 0.01, which is going to be 80. That's because we have the very different dissimilar evaluation and logging policies. That's the problem, right? That's the source of high variance. And here's how the SnipIPS estimator working. So again, this estimator doesn't use 1 over n, the typical notation. It uses the 1 over sum of importance weight. So we still see the huge importance weight is a numerator. It doesn't cut off. It doesn't, clip the importance weight. So we see the 80, right? 0.8 over 0.01 in the numerator. But the changes is in the denominator, right? The denominator is now the sum of importance weight. So if there are some huge importance weight in the numerator, the denominator is going to be also huge, meaning that we're going to have a moderate final estimation. So this is a trick used by SnipIPS estimator. We call this like a rescaling or sometimes a self-normalizing technique, right? And somewhat surprisingly, this estimator is still consistent. So meaning that if we have infinite sample of data, and if we use this SnipIPS estimator, we can still know the true policy value, right? That's great. It is actually not unbiased, but the difference is tiny when we have infinite, when we have a very large sample. So that's the power of the self-normalizing technique. And also there are some nice theories behind. Showing the SnipIPS estimator is very stable. You can just think of it as like, we can get some lower variance estimate compared to the IPS estimator. Thanks to this rescaling or self-normalizing technique. That's good. And what I think is great about this estimator is that there's no hyperparameters, right? We don't have any lambda hyperparameter. We don't have any, the reward predictor, meaning that we don't have to, solve the supervised machine learning, or we don't have to tune any hyperparameters when we use this estimator, which is great, I think, for practitioners especially. And also it works pretty well. So let's see some simulations. I think always the best way to understand how estimators work is to do some simulation and get some results. And let's do that again. So here is a result from exactly the same synthetic simulation platform, exactly the same synthetic data from the previous section. So the x-axis is just the number of samples in the log data. And the y-axis is the mean scale error in off-policy evaluation. So lower the mean scale error, the better as our off-policy estimator, of course. So we still see a bias variance trade-off of the IPS and the direct method. And what I did here is just additionally compare the 2 modified versions of IPS. The ClipIPS estimator in the purple line and the SnipIPS estimator in the gray line. So let's look at the purple line first. So you may see a little bit advantage of the ClipIPS estimator over the IPS estimator in the small sample case. So this is the power of the clipping technique, of course. We have some variance reduction effect by using this clipping IPS. But you may think that the difference was advantage is very tiny, right? So what I found here is that it was very difficult to tune hyperparameter lambda of the clipping estimator. So actually, I intentionally tried to do much better than the IPS by optimizing the lambda hyperparameter of the ClipIPS estimator, because I can do that because this is just a synthetic environment, but I found it very difficult. So it's very sensitive to the choice of hyperparameter. But how about the other one? So the other estimator, the SnipIPS estimator, is clearly working well, right? So it is, of course, consistent, keep decreasing the MSE with increasing samples, which is great. And also it is competitive with the direct method, which is a low variance estimator, right? So which is great. And also, again, what I think is great about this SnipIPS estimator is that I was able to get this result without tuning any hyperparameters. Well, I can't tune any hyperparameters because it simply doesn't have any hyperparameters, right? So I think it's much easier to use SnipIPS estimator. So there are just the two modified, kind of heuristic versions of the vanilla IPS. So there is the other approach. And this is the hybrid or the combination of two extreme estimators, the direct method and IPS, and which is the doubly robust estimator, right? So this is the hybrid of the two estimators. And I think, in my personal opinion, I think this is the most popular estimator in the policy evaluation community, and I believe some of you agree with that. And so when you look at some, policy evaluation papers on Google search, I guess you find many papers having doubly robust in their titles. So there are some reasons making doubly robust so popular estimator in the community. So first reason, I think there are some nice, great theories behind. So very roughly speaking, it is unbiased and consistent, and also it has a kind of variance optimality, which is great. And the other reason, I think, is that this is not so difficult to understand and implement, right? So of course, the original IPS is just a weighted empirical average. It is, very easy. So of course, doubly robust is a little bit difficult than the IPS, but I think it's still, reasonable, right? It is not so difficult to understand and implement in practice. So let's look at the definition. So we basically have two terms. Of course, first term, second term. And the first term is just a direct method. The model-based, one of the two extreme estimators. So let's put the direct method as a baseline here. So the good point about direct method is that it is very low variance by using the reward predictor, R hat. But it could have huge bias, depending on the quality of the reward model. And in industrial recommender system, I think reward is always paired with very sparse. So it's very difficult to approximately, accurately approximate this expected reward function. That's the problem. So what doubly robust is doing is that, luckily, we have some reward observations in the log data, which means that we can, do some correction to the estimation error of the reward predictor by putting the second term as a correction term, right? But we have to care about the bias in the observation, the reward observation, because the reward observations are observed under the login policy. So doubly robust is also using the importance weighting, the pi e over pi now. And then, so this estimator uses the reward predictor, but it is still unbiased and consistent because it, wisely, optimally using the correction term or the importance weighting, right? Which is good. It doesn't break any favorable property of the IPS estimator, even if it uses low variance, possibly high bias reward predictor in the first term and also in the second term area. And the other great stuff is that it has the potential to achieve optimal minimal variance among many possible reasonable estimators. This is kind of an informal statement, but you can just think of it as like, this is the optimal way of combining two extreme estimators. And also, in most cases, this doubly robust estimator has lower variance than the IPS estimator without breaking any favorable condition of the IPS estimator, which is great, right? So that's the main reason, I think, making this estimator so popular in the community. And let's look at the simulation result again, of course. So I additionally compared the doubly robust, the theoretically principled estimator here, the other experimental setting, the baseline, all exactly the same from the previous result, the previous rise. And you see that it works. You see that the theory is working, right? So the yellow line, the doubly robust, it does reduce the variance of the IPS, and it is competitive with the direct method, the blue line, even in the extremely small sample case, which is good, right? And it slightly improved the SnipIPS estimator, the gray line, okay? So here's a basic comparison over the 5. So we saw like 2 extreme estimators and 2 modified versions of IPS. And the final one here is the hybrids of the 2 extreme estimators. So what's your impression on this experimental results? So maybe many of you may think that, so looking at this result, so the yellow line and the gray line are doing great, right? They are consistent and competitive with the direct method, meaning that maybe they are just enough to completely solve seemingly difficult off-policy evaluation problem. That might be your impression on looking at this result, right? So I kind of partially agree with this kind of statement. So I do like the theory behind W robust, and I think SnipIPS estimator is also great, especially for practitioners. Again, it is very competitive with the theoretically optimal W robust, and also it is also consistent. There's no hyperparameters, right? So that might be your impression. But it's always difficult to draw this kind of too simple, simplistic comparison on the method comparison or algorithmic comparison, right? So what I mean here is that, look at this result. Actually, these estimators are doing great. That's true. But there are some other settings where these estimators can drastically fail. So we have to be careful about drawing too simplistic conclusion from one bit of a toy synthetic example to toy synthetic data or toy synthetic experiment. So let me introduce another interesting experimental result here. So we have 2 results. Let me say like the left-hand side and the right-hand side result. But actually, the left-hand side result is exactly the same result from the previous slide, right? So I just changed the scale of the y-axis, the mean scale error, because I just wanted to compare the 2 results with exactly the same y-axis. So the new result is just the right-hand side one. And you may think that we see a completely different phenomena, but actually these results were obtained from almost the same experimental condition or experimental data, right? So I just changed the one experimental configuration to produce the new result, and which is the evaluation policy. I think it's quite common to apply off-policy evaluation to several different evaluation policies, maybe having different hyperparameters in practice, right? And then we can pick the best hyperparameter among several different candidate evaluation policies without having A/B testing. That's, I think, one practical usage of off-policy evaluation in practice. So I just tried to apply 5 different off-policy estimators to 2 different evaluation policies here. And the evaluation policy of the right-hand side result is a very divergent policy from the login policy by now. And the divergence between 2 policies, the evaluation and login policies, are now measured by the maximum importance weight. So importance weight is just the ratio of the 2 policies, the pi e over pi now, which is used in, of course, IPS. And the maximum importance weight is simply the maximum observed importance weight is the log data. And the larger the maximum importance weight, the more different the evaluation policy is from the login policy. And we see that the right-hand side result has a much larger maximum importance weight compared to the left-hand side result. So this means that the right-hand side, the evaluation, the login policies are pretty similar, but the other side are the very different divergent policies. That's the only difference. The other experimental condition, the experimental configuration, exactly the same between the 2 experimental results, and I got this result. And looking at the right-hand side result, we see a completely different observations. That now the blue line, the one of the extreme, very old, ancient estimators, the biased estimator, the direct method, is now the universally the best estimator in the right-hand side result. So that's the critical difference, I think. So what I want to say here is that, looking at the right-hand side result, maybe you may think that, that just, the W robust and the SnipIPS estimator are just enough to completely solve off-policy evaluation, but that simple statement might be wrong here. because I just changed the one evaluation policy, and now the direct method can now be the best. For example, when the policies are greatly divergent ones. So another maybe impression here is that we should be able to do better in the challenge, let me say the challenging setting, because now the bias estimator is the best estimator, right? So there's a new motivation. So let me summarize a little bit the so far contents. So we have two extreme estimators. There's a notorious bias finance trade-off. So researchers have been aiming at reducing variance of the IPS estimator. And we have two approaches, the modified version of IPS and the hybrids of the two estimators producing doubly robust. But as we saw in the previous experimental result, I mean the right-hand side result, so the direct method can still be the best in some cases, but in some challenging setting, let me say. So there are some factors making off-policy evaluation much more challenging, such as the small sample size, which is difficult, the large, huge action space, and also the greatly divergent two policies. Those factors making off-policy evaluation much more challenging problem, and the challenging problem, as we saw in the previous slide, the direct methods, the biased estimator can still be the best, meaning that we want to do better. We should be able to do better. We want to beat the simple direct method, right? That's the recent motivation, being addressed by many researchers in the past, maybe 2 or 3 or 4 years. So what can we do here? And the current solution taken by recently the researchers in force evaluation is, let's consider the variance or the modification to the doubly robust. I think it's a quite natural direction taken by researchers. So we have two extreme estimators again at the first place. And then we think of a modified version of IPS or variants of IPS producing SnipIPS, for example. And right after that, we came up with, let's do the hybrids. And then we found the optimal hybrid combinations, I mean the doubly robust. So why not now consider the modification to the vanilla doubly robust? I think it's a very natural direction or the way considered by recent researchers. And actually, there are some variants of the doubly robust in recent literature. And I don't have time enough to go through every existing estimators and every details in this tutorial. So if you're interested in details, please just click the link and you can refer to the paper. But let me now just introduce the most recent estimators in the, at least in the contextual value setting, which is the doubly robust with optimistic shrinkage estimator. But again, the name of the estimator is pretty wrong, so let me just call this estimator the shrinkage estimator. I think it's pretty easy, right? Shrinkage estimator. And this estimator is, basically totally based on the vanilla doubly robust, but there is one single modification there. So here's the definition. We see two terms, and the first term is exactly the same, the direct method. And the second term is basically the correction term. But we see, the huge difference in the importance weight input. So I just simplified this notation here. I'm now using W to represent the importance weight pi E over pi now. I just wanted to simplify the notation. So I think it's much more easier to compare the two estimators. I mean, the vanilla doubly robust and the newly introduced, most recent shrinkage estimator. So almost the same. So the first term exactly the same. We have a second term, the correction term. But the only difference is in the importance weight input. So the doubly robust, of course, uses the pure, the true importance weight, which is now denoted as W. W is just the pi E over pi now, of course. But the only difference is like the shrinkage estimator is somehow modifies this true importance weight into this, kind of a little bit complicated one, right? And lambda is, again, the scalar value hyperparameter, and W is true importance weight, right? So I think it is a little bit difficult to, have a clear interpretation on what this modified importance weighting is doing here. But there are some nice theories behind. Again, if you are interested in more detail in theory, you can just go to the reference paper 19. I think it's a great paper. But simply speaking, there are some, this modified version of importance weight leads to a nice bias trade-off in the challenging setting. So I think the motivation is very clear. We just want to do better in the challenging setting. We want to beat the direct method in the challenging setting. And this modification is, used for, tricks or used for tools to do this, right? So why not do some simulation again? So I just additionally compare the shrinkage, the most recent estimator here, the green line, and let's look at the first. Let's look at the easy setting first, and you see that the green line, the shrinkage estimator, is clearly doing well. It works almost the same as the yellow line, the W box, and also the SnipIPS estimator, the green line, right? But this is just the easy setting. Our main motivation here, our main interest is the performance in the difficult, the challenging setting, right? So let's look at the challenging setting, result in the challenging setting here, and yeah, it's doing well. It's doing great. It works pretty well. Even when the two, the evaluation and login policies are greatly different, which is literally the challenging setting for all the OffPolicy estimators. But this is the main motivation of the recent advances, and the most recent estimator, the shrinkage estimator, is doing pretty well in the challenging setting. That's the recent advances in the standard OffPolicy evaluation. So let me now again compare the two results. So let me emphasize again that the right-hand side result it's pretty challenging for all the estimators because all the estimators have worse result compared to the right-hand side result. So we can compare the two results because we now have exactly the same scale of the y-axis. But again, the shrinkage estimator, the green line, it's good in the easy setting, and also it's doing great in the right-hand side, the challenging setting. It is outperforming the other estimators, including the direct method, the blue line. Okay. So what's your next impression on looking at this additional result? We have a nice additional result, and what's the impression of that? So you may think, many of you may think now that maybe the shrinkage estimator, the green line, is just enough. Why not just use shrinkage estimator for all the possible situations? Because it is doing good in the easy setting, left-hand side, and it's also doing great in the challenging setting. Why not just use this green line, the shrinkage estimator, for all the possible situations? That might be your impression now. Again, I kind of agree this kind of statement. Of course, the shrinkage estimator is a great, the very useful estimator, of course. But let me emphasize again that, that there's no free lunch in OffPolicy evaluation. There's no single winner. So what I want to talk in here is like, the shrinkage estimator seems to be a very favorable estimator here, but it does have some disadvantages over the other estimators. So let me introduce one final figure, the single figure in this section. So I created this figure myself, but I love this figure myself because there are lots of interesting observations and insightful information all in this one final figure. So I just changed one additional experimental condition to produce this figure, which is just the number of sample. I just increased the number of sample to over 50,000, right? So in the previous experimental result, we just have 6,400 log-money data at most. But here, I just increased that number to over 50,000. That's the only difference between this one final figure and the other previous results. And we can see a lot of interesting results here. So the first important theoretical property is the consistency. A consistent estimator can tell us the true policy value when we have infinite sample of data. So that's kind of a necessary condition for a good OffPolicy estimator. And there are three consistent estimators in this tutorial: the IPS, SnipIPS, and the W robust, the red and gray and the yellow lines. And we clearly see that these three, red, gray, and the yellow lines all keep decreasing the mean scale error with increasing samples. They are converging to the true policy value meaning that the consistency is now clearly verified empirically, right? We clearly see the consistency, which is interesting, right? But this means, in turn, that the other three estimators are actually inconsistent. So this is one possible drawback of the most recent shrinkage estimator. So shrinkage estimator is actually inconsistent, meaning that it does have remaining bias even if we have infinite sample of data. Why? So it's simply because it doesn't use the true importance weight. It somehow modifies this importance weight to get some advance in the challenging setting, meaning that it loses the consistency and actually unbiasedness from the vanilla W robust. So they're always trade-off, right? So we see clearly the inconsistency again. So we see the three flat lines. So the purple line, the ClipIPS estimator. The blue line, the direct method, of course, inconsistent. But there's another, the other flat line, which is the green line. And this is the shrinkage estimator. And it actually beaten by the W robust and the SnipIPS estimator in the very large sample case, meaning that it is not consistent. There is also another interesting observation, which is the optimality of the W robust. So the yellow line is the W robust, and it actually conversion to the true policy value faster than the other consistent estimator, including the SnipIPS estimator. This is the optimality observation of the W robust. Okay? So you may think that the difference is kind of tiny, but this is exactly what the theory says. The variance optimality of the W robust. And the final note, final observation here is that shrinkage estimator is still very useful. It does great in this, the challenging setting. So again, we can learn a lot of stuff from this one final figure. I love this figure myself. So there are some takeaways. So let me emphasize again that, that there's no single winner. There's no universal winner in OffPolicy evaluation. So we introduced 6 different estimators in this tutorial so far. So what is important here is that we have to understand the definitions and advantages, disadvantages of the possible estimator choices, and then we should be able to make right choices on which estimator to use in practice. So of course, every company data, every application, every business, every recommender interface, I don't know, are all unique. So the best estimator should change depending on your application. That's true. So we have to understand the motivation and properties of these basic choices. And then we're going to have a more clearer view on which estimator to use for our application-dependent stuff. And that's one takeaway here. And the other takeaway is actually my personal recommendation or my personal view on this final figure. So you may have some different intuition or different impressions, so I'm happy to talk with you if you have some different stuff, different recommendation or different intuition during the coffee break or maybe right after the tutorial. But my recommendation here, or my view here, is that there are 2 useful estimators in the community right now. And the first one is exactly the SnipIPS estimator, the gray line. I think it's just enough to use the SnipIPS estimator for the easy setting, when we face the easy setting, right? It is pretty good in the challenging setting again. It is competitive with the theoretically principal optimal W robust. And again, what I think is great here is that there's no hyperparameters. So we don't have to solve supervised machine learning problem. We don't have to train any hyperparameters. And we can get this kind of gray line result. So I think it's just enough to use this estimator for the easy setting. But the problem here is that it can fail drastically in the challenging setting. So I think the shrinkage, the most recent estimator, is going to be one additional useful choice. So it is very helpful and useful in the challenging setting. It's clear. So I think these are the 2 useful choices. That's just my view, my personal recommendation. Maybe one additional disadvantage of the shrinkage estimator is that there are many hyperparameters to be tuned for the shrinkage estimator. But I am going to introduce how to tune hyperparameters from only available information for off-policy evaluation estimators in the next section. So please wait for that for now. So you may be interested in some simulation result here. And you can just click the link, and then you can go to the GitHub repository, and then you can just try, and you can just easily reproduce the simulation result, all the results in the slides. And also you can try different synthetic setting, maybe relevant to your application. I think it's very important and enjoyable to see how estimators work in your setting of interest. So please try that. And actually, it's very easy to reproduce the result and try some other setting with my implementation, because all implementations are now based on the OpenMuddy pipeline, which is a Python package for off-policy evaluation and learning. And it helped a lot in my creating tutorial content. It is very, I think, a great package. And I'm going to introduce what it is, how we can accelerate our research, and how we can accelerate our study on off-policy evaluation using this package in the second half of the tutorial. But let me just say here that all the implementation are very easy to modify because of this package. Okay, so that's my first section. And the next section is going to be the final topic of the first half. So let me change my gear a little bit here, and let's see more recent advances in off-policy evaluation, or maybe off-policy evaluation for more practical settings. Okay, so that's a little bit different topic. So far we've seen like the standard evaluation setting. So there are some implicit, simplistic, neglected assumption there. So there was only a single discrete action. And in some simulation studies, the hyperparameters were already arbitrarily chosen by me. And there was only single login policy and no distributional shifts in the environment. So next in this section, we're going to look at the more practical challenges right now being addressed by the researchers or in the literature. So I don't have ultimate solution myself in the topics or the problems in this section. They're just the ongoing work. But I think it's beneficial or useful to have some, to know what's going to be the challenges, what's going to be the issues when we try applying off-policy evaluation to a practical setting. So that's the motivation here. We don't see any ultimate solution here. The motivation here to understand what's going to be the issues, what has to be resolved, what has to be addressed in the near future in the community. And that's the motivation here. So I'm going to talk mainly about two topics in this section. The first is, I think, very relevant to the RecSys community, which is going to be off-policy evaluation for combinatorial action setting. And the final topic of the first half of the tutorial is going to be how to automatically tune hyperparameters for off-policy evaluation from only available data. That's going to be also exciting, very recent topics, I think. So let's look at the first topic, the combinatorial action stuff. So again, so far, we assume that a policy, an algorithm, chooses only a single discrete action from the pre-given, predefined action space. So here's a data generation process for the standard setting. So we first observe context vector X from the environment, and then a policy pi, which is a conditional distribution over action, picks a single discrete action A, which can be a fashion item or YouTube video, whatever you want. And we finally observe reward variable R, which is also application dependent. You can define the reward variable, whatever you want again. But look at the more practical setting. We always face the combinatorial action space, right? Nearly always or very often, we have to address the kind of combinatorial action space, meaning that a policy has to choose a list of set of discrete actions at the same time. So for example, in this YouTube recommendation example, of course, we see a list of different, several discrete lecture video recommendations. So this is a combinatorial. A fashion item, of course, we see 3 different simultaneously presented actions in the same recommendation interface. That's combinatorial. And of course, in the Google search, we have some documents. presented to a single given query. This is also combinatorial, right? So the topic of this section is going to be how, what's going to be the challenges, what's going to be the issues when we try applying off-policy evaluation, offline evaluation in general to this kind of, very prevalent combinatorial action case in practice. So we have to modify our formulation a little bit here, of course, because we are facing a little bit different problem. But I think it's not so difficult. So what we have to introduce is just a k, the integer variable here. This is just differentiate the different positions in our list of recommendations. So in this toy example, we have 4 different positions in our list of recommendations, and we have to somehow differentiate the each position. So we need this new notation. That's it. So K1, K2, K2, K4, right? I think it's not so difficult. And also we have some actions, A1 to A4. So A1 is an action or discrete action chosen by the algorithm for this particular position 1, the top position. And we also have some reward observations. And for example, R4 is a reward observation observed at that particular position 4, fourth position, the bottom position in this example, right? So that's the only difference. So here's some difference in notation in the data generation process, of course. So we first observe context vector X. This is the same. And then a policy pi select a action vector A, or vector A, yeah. This is no longer the action variable. So action vector containing, A1, A2 to A capital K. So we have to, have some, K different discrete actions in the combinatorial action space. And finally, we observe a reward vector R. This is a list of click observations. So it contains like R1, R2 to R capital K, the same as the action vector, right? So that's the only difference. So let me also check what's going to be the estimation target or estimate here. I think it's always very important to clearly define what's going to be the estimation target, what's going to be the estimate when we do some statistical estimation problem. So here we want to estimate the policy value or policy performance of an unseen evaluation or a new policy, right? So this is the same motivation as the standard of policy evaluation, of course. So B pi E is a policy value, and pi E is a new policy. But we want to evaluate this new policy without deploying this policy. Well, before deploying this policy to the real field, we want to have the confidence in this performance of the new policy. And the policy is now defined as the expected reward obtained by running evaluation policy to the real field. So this is basically the same from the previous standard setting, but there's some difference in notation. So the first notable notational difference is that the evaluation policy is now the distribution over action vector, not the action variable, right? So we have to have a distribution over the combination of action. That's one difference. And another difference is that the reward distribution is also over the reward vector, not the reward variable. So reward is also, we have a k different reward observations, right? That's a tiny difference here. But also, let me now note that the right-hand side, the reward, is now not a vector, the scalar value, right? So what I did here is that I wanted the policy value to be a scalar value, right? If the final policy value is the vector value, there might be an independent research interest, right? They're going to be like a multi-objective recommendation, what kind of stuff. That's an independent interest. So I want to keep it simple. I just wanted to focus on the statistical estimation of policy evaluation problem. So I now summarizing the k reward observations in a list of recommendations into a single scalar value. That's what I did here. And there are some possibilities to summarize the k different reward observations into a single scalar value. And I think the most popular, simplest way to do so is the weighted sum of position level rewards. So Rk there is a reward observation at position k, particular position k, and alpha is just a design parameter. We can define the weight as we like. This is just a weight, the importance of each different position. So there are some typical choices in the alpha. So of course we can set a uniform weight, And then the summarization reward should be the number of clicks in the k different reward observations. That's it. We can also define the discounted cumulative gain or like precision measures by just customizing the weight, right? So the important point here is that we can just cover a wide range of famous information retrieval metrics by just customizing the alpha weight. So this is a very usual way to summarize k different reward observation. I guess most of you have used this kind of reward summarization. And of course, this is not the only way, but I think it's very simple way to do so. So I just use this way to summarize the reward from now in the slides. So that's one difference. We have to somehow summarize the reward into a scalar value. So then let's talk about how to do off-policy evaluation in the combinatorial action space. So maybe the most naive way or the simplest way to do off-policy evaluation in the combinatorial action setting is, why not just use an IPS estimator again, right? I mean, the combinatorial action is still a discrete action. We can just differentiate all the different combinations, and this is still the discrete action problem. So we can just naively apply the vanilla, the original IPS estimator, to get an unbiased and consistent estimate, even if we face a combinatorial action space. That should be true, right? So this is the IPS estimator for the combinatorial action setting. So this is just the weighted average of the reward observations. Of course, we see some difference in notation, but the concept is exactly the same. The weight is importance weight. The importance weight is now the over the combinatorial action vector. That's one tiny difference in notation, but what it does is just the same. And the reward observation is now the k, the summarization of the k different reward observations, but this is just the weighted average of the reward observation. So this is the naive application of the IPS estimator to the combinatorial action setting. We should be able to do this because combinatorial action is still a discrete action. So let's compare the standard IPS and the IPS for the combinatorial setting. This is, for me, exactly the same estimator, but we see some difference in notation, right? So the IPS is just the weighted average of the reward observation, and the weight is importance weight pi e over pi now, but the action is just not a combinatorial, right? This is just a single discrete action for the vanilla case. The combinatorial action case, that's our current topic. And this is still weighted average of the reward observations, but the importance weight is over the combinatorial action, and the reward is now the k different, the summarization, but this is a scalar value now, right? So this is, the same. So meaning that the theory should still apply, meaning that, just naively applying the IPS, we should be able to get an unbiased and consistent estimate even for the combinatorial action, the very practical setting, right? That's my statement here. So does it mean that the mission has already been completed for the combinatorial action setting? Because we now have the unbiased and consistent estimate for the combinatorial action case, meaning that if we have infinite sample of data for the combinatorial action setting, we can still know the true policy value. That's the statement here, and the theory should apply. Mission completed. But actually, the thing is that this naive application of the IPS to the combinatorial action setting doesn't work at all in practice. Why? What's going to be the problem here? What's happening? So let me illustrate what's going to be the problem in the combinatorial action setting. The problem is simply that the action space is going to be notoriously, ridiculously huge. So let me illustrate that using, again, the toy example. So we have 100 unique actions and the 3 positions. So we have the 3 positions like this. And so what we have to do here is pick the 3 different actions from 100 unique actions, and then we reorder the 3 actions, and then we have one list of recommendations. That's the situation here. And can you guess what's going to be the number of all the possible combination of the 3 actions for this setting? And the result is like the over 16,000. So I just counting, the 1 to 3, 1 to 4, 2, 98, 99, 100. That's all the possible combinations in this setting. and the resulting number of all the possible combinations is going to be over 16,000. So some remarks here. In most of the standard OffPolicy experiment, researchers are just using the very tiny action space, having only 10 or 20 actions. This is, of course, a useful result. It's going to be a useful result, but in industrial recommender system, 10, 20 action is not that usual. We have to have this like a combinatorial action space. And also the thing is that the standard OffPolicy evaluation doesn't work at all in this kind of combinatorial action space because maybe you may remember that the number of action is one of the main factors making OffPolicy evaluation much more challenging. Right? That's one problem. There's another similar problem. So let me consider another, almost the same, for example. So we have 100 unique actions, which is the same. The only difference is that we now have 7 more positions in a recommendation interface. So what we have to do here is to pick 10 different actions from a unique action pool. And then we reorder the 10 actions, and then we have a final list of recommendations. That we have to do here. And then, can you guess, again, what's going to be the number of all the possible combinations is going to be for this problem? The former problem, we have about 16,000 actions. And how about the next? A little bit difficult, little bit different problem. What the number of action is going to be? And the answer is this number. And I don't even know how to express this number in English, right? I know the trillions and millions, but maybe it's more about trillions. So the thing is that the combinatorial growth is much faster than the exponential growth, meaning that this is still a tiny problem for industrial recommender system, right? In the industrial recommender system, we always have hundreds of millions of unique actions, meaning that the resulting combinatorial action space is going to be very huge or ridiculously, notoriously huge. That's a problem. So let me summarize. Sorry, that's another slide. So let me illustrate what's going to be the problem with a huge action space in OffPolicy evaluation with a different perspective. So let me assume that the login policy is now uniform, meaning that the pi now is just a constant, 1 over the number of combinations. So this is just the weighted average of the reward observations, the vanilla IPS. And we see that the 1 over pi now in the importance weighting definition, meaning that in definition, we always have the number of all the combinations in the definition of the IPS, even if when the login policy is uniform. So this is the source of huge, unbelievably large variance of the IPS. This makes the IPS totally useless estimator in the combinatorial action setting, even if it is unbiased and consistent. That's the problem. Okay, so there's a critical variance issue. Let me say combinatorially large, combinatorially huge action space is a problem. And let me emphasize again that this is still an ongoing problem. Of course, we want to do good OffPolicy evaluation in the combinatorial action setting, but it's still very challenging to do accurate OffPolicy evaluation in the combinatorial action setting. So there's no ultimate solution here. But there's one possible, promising, interesting approach in the recent literature. So let me introduce some of the direction there in this tutorial, which is to introduce some assumptions on a user behavior. I mean, how user behave in a list of recommendation. And then we should be able to make the combinatorial action space much more tractable, or meaning that we can get some variance reduction. Okay? So some of you may know, or some of you may are aware of the literature named click modeling in the information retrieval literature. And click modeling basically, assuming some behaviors on a list of recommendations or in a web system. So I think this kind of recent approach can be seen as a hybrid of the click modeling in the information retrieval literature and the statistical estimate, statistical OffPolicy evaluation problem, right? By combining the knowledge from the click modeling and the statistical OffPolicy evaluation problem, we can do a much better OffPolicy evaluation in the combinatorial action series. That's the basic idea here. So let me introduce just the 2 estimators in this direction. And the first estimator in the direction is independent IPS, or just IIPS in short. So this estimator is based on one of the user behavior modeling named item position model, or just an independence model. I think this is a very strong assumption, but it is very useful in reducing the variance of the IPS estimator in the combinatorial action setting. So it just assumes that users interact with the items totally independently, meaning that when we look at the third reward observation, this assumption assumes that this reward is only dependent on the corresponding action A3. So we now ignore all the possible interaction from the other position. That's what this assumption is saying, right? This is pretty strong, but this is very useful in reducing variance. So this means that when we look at the case reward observation, we can say that this is totally independent of the action and the reward of the other positions. So this is based on the assumption of the item position model. So we can use this assumption to make a better estimator, right? That's the idea here. And this is the resulting estimator, which is the IIPS estimator. And this is, again, based on the item position model. And here's the definition. We see some notable difference from the vanilla IPS. I think one notable difference here is that the importance weight is now just on the action variable, each different action. We don't see anymore the action vector here, meaning that we now can ignore all the possible combinatorial effects in the list recommendation thanks to the independence assumption, right? And one also interesting interpretation on what this estimator is doing is that, so now the importance weight is inside the summation, meaning that this estimator solves the k different OffPolicy problems, each corresponding to the different position totally independently or separately. And after that, it summarizes the k different OffPolicy evaluation result, and it leads to the one final OffPolicy evaluation result. That's one interpretation on what this estimator is doing. And this estimator can do that because of the independence assumption. We can just split the combinatorial action space into k different independent separate OffPolicy evaluation problems. That's the trick here. And there's some nice theories. So this is unbiased and consistent under this assumption, right? If this assumption is satisfied in the real world, then this estimator is going to be unbiased. And also, it greatly reduces the variance of the vanilla IPS because we don't consider the importance weight over the action combination anymore, thanks to this assumption. And one downside here is that it could have huge bias, high bias, not variance, huge bias, depending on the divergence of the assumption from the real user behaviors. So this is, I think, another type of bias-variance trade-off, now depending on which type of user behavior assumption we choose. Okay, so here's the, again, the intuition, how the IIPS estimator reduces the variance of the vanilla IPS. So the problem with the vanilla IPS is that we always see the number of actions in definition, meaning that this vanilla IPS is going to be very unstable estimator in the combinatorial action setting because the action space is now combinatorially large. But when we use the independence assumption and the IIPS estimator, we don't take into account the combinatorial effect anymore, meaning that we can just think of the, the unique action separately or differently, meaning that we just see the number of unique actions inside the definition of the IIPS. So that's the intuition on how this estimator reduces the variance of the vanilla IPS, leveraging the additional user behavior assumption. So that's one interesting approach in the literature. And here's a view. We have now another two extreme estimators. One is the vanilla IPS, which does not use any assumption, meaning that this estimator is now universally unbiased if we know the true login policy, of course. But the problem is that it could have huge variance, right? So there is the other extreme, which is the IIPS estimator. This is now based on the independence user behavior modeling, which is very strong. So we could have huge bias depending on the real user behaviors, but it is very useful in reducing variance, right? So this is, again, another type of bias variance trade-off. Now, depending on what kind of user behavior modeling we use to create a new off-policy estimators. And the one final estimator I want to introduce here is the middle of the two estimators, which is a very recent estimator, which is the reward interaction IPS or RIPS, which is, I think, proposed in last year KDD, which is a very recent one. And this is now based on the Cascade user behavior modeling. I think it's a very famous user behavior modeling in the information retrieval literature. And it assumes that users now interact with the items in the list recommendation sequentially or one by one from top to the bottom position, right? So this means that when we look at the same, the third reward observations, we have to care about the interaction from the same position and the actions from the higher positions, right? Because just, simply because now users are coming from the top. So we can ignore the effect from the, the action of the bottom position, right? So we can ignore some interaction in the list of recommendations based on this assumption, meaning that we can get some variance reduction, right? And also, this is much more reasonable assumption compared to the previous independence assumption. And this is a resulting estimator based on the cascade modeling. And this seems to be a little bit complicated. But the important point here is that, so there's a product term. This is just the importance weight. But the product is now taken from the top position from the case position. When we look at the case position, meaning that we don't have to care about the importance weight for the the k plus 1, k plus 2 to the capital K, the lower position. When we look at the case position, again, now users are coming from the top to bottom, right? So that's the trick used in here, the reward interaction IPS, and some theories. So this is unbiased and consistent when now the much more reasonable cascade model is true. And another great stuff is that it greatly, again, reduces the variance of the vanilla IPS because we can now ignore some interaction in our list recommendation. But it could have larger variance than the independent IPS because we now consider some more interactions or interactions in the list recommendation compared to the very simple independence assumption. So yeah, here's truly bias variance stuff, or the trade-off stuff, right? So we see 3 estimators in the combinatorial action case, and this is another type of bias variance trade-off. Now, depending on what kind of user behavior modeling we use to design a new policy estimators. So we see a no assumption IPS, which is unbiased but have huge variance. The other extreme is IIPS, which is a very strong assumption, so could have high bias. And there's a nice middle of the 2 extreme estimators, which is the reward interaction IPS. And this is now dependent on the cascade modeling. And maybe some of you may know that there are some other click modeling, for example, the user browsing model or dynamic Bayesian model. There are some others. So if you are interested in that, you may be designing a new estimators by yourself by combining some other user behavior click modeling and the policy evaluation stuff, and then you may be able to write a new paper. So please do that if you're interested. But there's, this is all the estimators existing now, I think. So this is the first topic, and the second topic is much shorter. So let me just briefly look at how to tune hyperparameters for the policy evaluation. It's going to be just 10 minutes or so. So let's go back to the standard world. There's no combinatorial stuff. It's too difficult. So let's go back to the standard stuff. But we still have some difficult topics. So one notable stuff is that we have many hyperparameters for off-policy estimators, right? So for example, the direct method, W-Worst have a reward model, reward predictor, meaning that we have to choose what kind of supervised machine learning method, such as the random forest, or support vector machine, of course. We have to pick the right choices on constructing the reward predictor. And the most recent shrinkage estimator have reward model and the shrinkage rate, the scalar hyperparameter value. So we have to change these estimators, optimally. And I would argue here that the hyperparameter tuning is very important in ensuring the accurate voice evaluation. So here is again a simple simulations. So all the 3 lines are just a shrinkage estimator, the same estimator, But I just changed the value of the lambda hyperparameter value from 1 to 10,000, and I got this result. And it clearly, you clearly see that hyperparameter selection is really, really important to ensure accurate policy evaluation. But the difficult point here is that it is always, we have to pick a good hyperparameter from only available data, I mean the log data from the login policy. That's going to be very difficult. So let me see why it's very difficult. So ideally, so this is going to be an idealistic criterion on how should we pick hyperparameters. So mean squared error is the accuracy measure of the policy estimator. So this is just the expected square distance between the true policy value and the policy estimate. Of course, the lower the MSE, the better as a policy estimator. So when we pick when we pick a hyperparameter, we want to minimize the mean squared error of the resulting estimator from the possible hyperparameter search space. And then this hyperparameter is going to be the optimal hyperparameter in terms of mean squared error or the accuracy of policy evaluation, right? So we want to do that when we choose policy evaluation. But the difficulty here is that, of course, the mean squared error is an unknown quantity. We cannot know the mean squared error because there's a true policy value. We don't know that. And also, we cannot take the exact expectation, of course. We don't know the exact data generating process. So this is an idealistic, we cannot implement this procedure, right? So we want to somehow make it implementable, make it possible. So the basic strategy here is, so let's first of all decompose the mean squared error into the squared bias and the variance. This is just an introductory statistics, I think. And the basic strategy of the reference paper there is that let's try to estimate the bias and the variance separately from the log data. And actually, the variance is much easier to estimate compared to the bias estimation. Because again, from the introductory statistics, the variance does not depend on the true policy value, right? The variance is just, again, the expected square distance between the policy estimate itself and the expected value of the policy estimate, meaning that we don't have to know the true policy value when estimating the variance. We can just have to take the sample variance or the empirical variance to estimate the second term. But the problem is the first term, right? So it does depend on the true policy value, right? So this is, again, the introductory statistics. The bias is defined as the absolute distance between the true policy value and the expected value of the policy estimate, meaning that we have to know the true policy value to accurately replace the squared bias term. But remember that we want to know the true policy value, right? We want, the reason why we are now studying policy evaluation together in the room is that we want to know the true policy value somehow from the log manifold data. But what this slide is saying is that we have to know the true policy value to estimate the bias term. So it's kind of a contradictory statement or argument, right? But there's a great trick, is that we can somehow estimate the bias of the policy estimator from the log data if we know the true login policy. So I think it's difficult to derive this bias estimator from scratch in this tutorial. But if you're interested, please look at the paper. I think it's not too difficult. I think it just takes a few hours to understand what's going on. So let me just introduce the resulting bias estimator and what the important components there. So the one important component of the bias estimator, the estimator of the bias, is that the deviation of the modified importance weight. So W is again the true importance weight. This is just the pi e over pi now. So this is used in the vanilla IPS or the W bus. And the W dash there is the modified version of modified version of importance weight. So we have several modifications. For example, the ClipIPS technique or the shrinkage. So this is just totally estimator dependent term. So the red part is just a deviation of the modified importance weight from the true importance weight. So this means that the larger the deviation of the modified importance weight, the larger the bias estimate. I think this is very reasonable because true importance weight leads to the unbiased zero bias estimate. So when we aggressively modify the importance weight, we should have larger bias. So that's what this first component is saying. I think it's very reasonable or intuitive. But there is another component, which is a blue part. This is the estimation error of the reward predictor. This is, I think, a little bit unintuitive to have this term in the bias estimator. But what it said is that when we have an inch-perfect, very accurate reward predictor, it just ensures the consistency or the unbiasedness of the estimator, meaning that when the blue part is very accurate, nearly zero, we can be aggressive when we modify the importance weight, right? So meaning that the ideal hyperparameter should depend on the quality of the reward estimator. So we should have the estimation error of the reward predictor in the bias estimate. That's what this second term is saying. But anyway, now that we have this implementable estimator for the bias term, I mean, we can calculate this from the log data, meaning that finally we have this implementable hyperparameter tuning procedure for off-policy estimators. So we just have to search the hyperparameter, or maybe the set of hyperparameters that minimizes the squared bias estimate plus the variance estimate. The variance estimate is much easier to have compared to the bias estimate. Bias estimate seemingly very difficult, but we somehow can do that with this estimator from the recent literature. And let's see the final simulation result in the first half. And I just additionally compare the shrinkage estimator, but now with the automatic hyperparameter tuning. So the gray line is actually implementable result in the real-world scenarios. I didn't use any unavailable information when I produced the gray line result. And we see that it works pretty well, reasonably. And of course, it should be tested for the more challenging setting. But I think this hyperparameter tuning procedure is going to be a good baseline. So the final question may be, you want to use hyperparameter tuning in your maybe off-policy evaluation practice. But the problem is that maybe we have to implement this from scratch, right? But maybe the hyperparameter tuning is a little bit complicated, and you may think that it may be difficult to implement from scratch by yourselves. But you don't have to do that. So again, let me introduce that the OpenValue pipeline, the Python package, has already implemented this very recent hyperparameter tuning procedure. So you don't have to go through every detail of this hyperparameter tuning procedure when you use that. You just import this OpenValue pipeline, and you are now ready to use this hyperparameter tuning. So you can automatically tune, for example, the shrinkage estimator or the W loss estimators when we use this package. And I'm going to talk about more in the second half about this package. And also the simulation code for the hyperparameter tuning is available now on GitHub. And that's it for the first half. Thank you for the little bit longer, maybe, first half. And we're going to have a coffee break. We'll be on schedule. So we're going to start the second half from 11:40 local time. Sorry, we have just 15 minutes. The next session is going to be from 11:40 local time. And we're going to remain here, maybe. So if you have some questions or some topics to talk, we're happy to do that. And of course, you are free to take a coffee break, of course. But if you have some great stuff, let's talk together. And thank you again for your attention.
Test. Okay. So yeah, welcome back. So the second half of the tutorial is going to be about how do we use these estimators that we saw in the first half to then actually do learning. And learning is really just the problem of evaluating a lot of different policy to find the best one. So just a reminder, we have our log data from the logging policy dnull, pynull. And so we have the context logged, we have the action that was taken by pynull logged, we have the reward logged that we got for this action, and let's also log the propensity, right? That's always a great idea. If you're actually building a system, log the probability with which the policy pi null actually took that action. So this is this contextual bandit feedback, and it's this data generating process that we had in the first half still. So we've seen how to take one new policy, pi e, and evaluate the performance offline, right? We answered this counterfactual question of, if we had used pi e instead of pi null, what would the performance have been? And we've seen many different ways of how to do this estimation. And we've seen also in some cases it's more difficult, in some cases it's easier. Now, can we use this to do learning? Can we find the policy that improves performance over pi null? That's what we're typically interested in, right? We want to use this data to do some new learning. We have the data from the system that we collected over the last months. That's pi null, data from pi null or d null. And we want to get a better policy. And we don't want to do online learning. We just want to use this old data because we want to do everything offline without exposing users to the kind of potential harms that comes from an online learning process. So how does this kind of learning problem actually fit into our taxonomy of machine learning algorithms? By far the most common one, so we have the kind of two dimensions here. There's online learning and batch learning, so online and offline learning. And there's full information data and partial information data. Full information data, I mean, somebody tells you what the right label is, for an example, or here somebody tells you what's the best product to present to this customer. So full information data in the batch setting, there's a ton of algorithms. SVMs, random forests, deep networks, right? It's an extremely well-studied problem. Same thing for full information data. We have the true labels for everything. We have the rewards for everything. In the online setting, lots of algorithms we have for that. Well-studied problem. If we look at partial information, this kind of bandit feedback, where we only get to observe the reward for the one action that we picked, or some other partial information setting, maybe just a few actions that we picked, then there's online algorithms for that. But we don't want to do that. We don't want to collect new data all the time. We just want to kind of reuse the data that we already have. So we're down here, right? We're in that quadrant. And so that's often called batch learning from bandit feedback. And that's what we want to do. And I would argue that this is probably the least explored space of the machine learning algorithms, and there's still a lot of interesting research to do there. So to state the obvious, what's our goal? A little bit more formally, we have our log data with the log propensities, these probabilities of taking the action under the logging policy, often called propensity. And now we want to find the policy from some hypothesis space, some policy space that we defined, let's say deep networks of a certain form, right? And we want to find a policy that maximizes the value, right? That maximizes the expected reward. So what we really want to do is we want to optimize online performance of our policy, but we want to do it purely offline with data that we already have. Because we can do it faster, we can do cross-validation, we can do all of these good things. And then only once we've kind of found a good policy, that's what we're going to put online. So here's the basic outline. I'll first talk about kind of model-based approaches to policy learning. And then point out some of the issues with that, and then go to model-free approaches and deal with some of the issues there as well. And finally, kind of connecting to what Yuta had in the end of the first section, talk a little bit about learning to rank as a special type of offline policy learning problem, where the things that we are the policy that we're learning is a ranking policy. And probably just talk about the first one here, not have enough time for that. Okay, so let's start with model-based policy learning. Again, that's probably the first thing that would come to your mind as well. So we have our log data, And just like for the direct method, when we do off-policy evaluation, we learn a regression model that would now allow us to predict the reward of any new context and any action that we will encounter in the future. So we trained this reward predictor, R hat, from the training data that we have, right? We've seen these observations here. That's just a regression problem. We train our R hat, and then if we have new users coming in, we can just impute what the reward would be of taking each of these actions. We've done that for the evaluation problem already, and the learning problem is almost trivial in this sense, right? Once we have accurate reward predictions, well, we just pick the action that has the maximal predicted reward. And that's, the best policy, at least we think that's the best policy. So that's just this very simple rule. Take the imputed rewards, pick the action that has the highest predicted reward. So like here, we would pick the action that has a predicted reward of 2, here of 3, here of 1, and so on. If our predictions are correct, if they're very accurate, then this is going to be a great policy. So here's, again, a synthetic example. It's kind of a mock news recommendation setting where we have a user profile, that's our context. We have 3 slots where we can put in news articles. It's synthetic, so it's all made up. And let's say we have just 7 candidates that we can place into these 3 slots. So it's not really a big combinatorial problem. It's just 7 choose 3 different actions that we can take. And we forget about the whole combinatorial part. We can just enumerate those. And then there's a reward function that we don't know in the simulation. It's our revenue. It's a complicated function that kind of is about the match between a context and the action here that produces the reward. And we have a logging policy pi-null that is pretty good. So we have an existing system that's pretty good at maximizing reward. And we make it a little bit more stochastic through a Plackett-Luce model, where basically we're randomizing a little bit so that we get full support. So here is the performance of the production policy, true revenue of 224 somethings, doesn't matter. And by introducing this randomization into pi-null for logging, right, we need to be a little bit stochastic during logging to get the, some probability that each of these actions actually gets explored. We lose a little bit of revenue, right? The randomness has some cost to it, right? But now we have log data that actually has sufficient support, that tries all of the actions with non-zero probability, and we can use that now for learning a better policy. So let's use this direct model method that we had before, learn a regression, and then pick the action that has the highest predicted reward. Here, it's a particular setup, used kind of a set of different methods, and then pick the one that has the best regression error through cross-validation. And unfortunately, the result is a little disappointing, right? If we take this policy that maximizes the predicted reward, the actual true reward is actually lower than the reward of the logging policy. So we haven't actually learned a better policy here. And that doesn't have to happen. I've kind of set it up this way. It can actually work, but if it doesn't work, what could be the reason for this? Well, one reason is that, if we are learning, we've kind of come up with these 2 features that we give into our regression model that let us learn a reward predictor. And we have these reds and these greens, and this is how our reward predictor imputes over the whole possible action space, right? And now what we're doing is, we're saying, let's pick the action that has the highest predicted reward, which is, this is the greenest action down here in the corner, right? So now it really matters whether our reward predictor extrapolates well, right? This corner is pretty far away from all of the kind of points that we actually know. And that our reward predictor extrapolates like that, instead of maybe extrapolating like that and making this red down here. It's really a choice of our model. And if we haven't picked our model well, this can go wrong, right? If you picked it well, it's going to be great. But if we didn't, it can easily go wrong. So there's this kind of issue of model misspecification, and there's a selection bias that comes from the logging policy. So we don't even have least squares optimality or anything like that. The second issue is maybe also a little bit more philosophical. To quote Wapnick, if you want to solve a problem, don't solve a harder problem first. And in a way, that's what we've done here. Because predicting the reward everywhere is actually a harder problem than finding the optimal policy. In the following way, right? Of course, if we predict all of the rewards correctly, it's easy to read off the optimal policy. But this is a harder problem than the optimal policy, if I just find the optimal policy, because if we have the optimal policy, we don't necessarily need the correct rewards, right? We can't read off what the predicted rewards are. The optimal policy just acts and picks the right action, but it doesn't actually need to cardinally predict what's the right reward. So arguably, this problem can be easier than reward prediction. So that's the idea behind model-free learning, where we don't predict the rewards, we actually directly search for the optimal policy because it's a potentially easier problem. So let's look at how this could work. How can we do model-free policy learning? And, well, basically we can do empirical risk minimization again. Empirical risk minimization says, well, here we have kind of a training reward or a training error. Here it's a reward. And what we want is we want to minimize or maximize training reward subject to regularization that prevents overfitting. And there's a good, lots of learning theory that tells us if we manage to optimize training reward, then we can also optimize, that also carries over to the test reward, right? And so in the principle, this is what most machine learning methods do. They do well on the training set because that gives us good generalization performance. So now how do we do this in this counterfactual setting, right, in this off-policy setting? And so we have to decide, what estimator do we use for training error? In supervised learning, it's pretty obvious, right? It's, well, the training error. But here we have to use something else. How do we regularize? Are we going to use deterministic versus stochastic policies? And then how do we solve that optimization problem, the training problem, basically? So let's start with the simplest case. So let's start with, we use the IPS estimator. That's our training error, or training reward, so to speak. It's an unbiased estimator, just like normally in supervised learning we have an unbiased estimator for our training error. And let's just use deterministic policies as a special case. So what does this then look like? And no regularization for now, just to keep it simple. That means this is the IPS estimator for deterministic policies, just puts probability 1 for the action that was, that's chosen by that policy. This is the indicator function that just gives 1 or 0. This is the probability under the logging policy, the propensity, and this is the observed reward. So we want to maximize this quantity. And if we just switch this with this, right, we get a problem that looks like that. And that's just a weighted classification problem. So basically it says we have these weights, the reward divided by the propensity, probability under the logging policy. And now what the algorithm tries to predict is what did the logging policy choose? Which action did it choose? And so in this very simple case, we can just use existing weighted classification methods for this. And so there are a number of different reductions that we can use. There are a number of nice ones implemented in VW or in Yuta's Open Bandit pipeline. And let's look at how this works. So we just translate it into a weighted classification problem. So estimator that we're using here is IPS, or you can do the same with doubly robust as well. Basically, everywhere where you use IPS, you can use doubly robust as well, because doubly robust is basically just an IPS where you change the rewards, right? You just translated the rewards by the regression model. The regularizer, there's actually some regularizer that prevent overfitting built into these classification methods. We're using deterministic policies, and we just use existing off-the-shelf methods. So what you get is something that's, again, a little bit better than what we get from the reward predictor, but it's unfortunately still worse than what we started out with. And again, that doesn't have to happen. Sometimes this works, but it can also go wrong, like it did in this case here. And again, let's think about why it went wrong, and to kind of unravel how we can actually get more and more robust learning. So the first one, approach one, had a problem with bias. The second, the model-free one, has a problem with variance. But variance is something that's easier to address. Variance is something that's easy to measure, and it's easy to control. And variance becomes smaller the more data that we have, right? If all else fails, throw more data at it, basically. So, but how can we deal with the variance in the model-free approach in a more principled way? So let's look at the slightly more general version where we have stochastic policies. And so then the empirical risk minimization training problem becomes, here I'm minimizing now reward. You can also maximize. It's minimizing a loss versus maximizing reward. Doesn't really change anything. You have the probability under the new policy that we are learning divided by the propensity under the logging policy. And we need to optimize that. So what's the potential issue that's happening here? So we're searching now over all policies in our hypothesis space, H here. And some policies are kind of close to the logging policy. For example, this is our logging policy pi null, this is pi 1, and this policy is pretty close. So if we do this weighting, you know, the importance weights, there's the size of the circles here, they're, you know, reasonable, right? So the variance is okay for evaluating pi 1. But there's probably this other policy, 237, in our hypothesis space, that's like way out there in the corner. And what happens is that it basically blows up the weight, the importance weight of this one point, and the variance is huge. In the right-hand side, it's basically that you're getting an unbiased estimate, but based on a single data point, right? The effective training set size for evaluating this policy is dominated by 1 point. So its effective training set size is 1. Here it's much more reasonable. You know, it's a number of points. So what's very different from supervised learning and this off-policy learning is, in supervised learning, for every hypothesis in your hypothesis space, the variance of your training error is basically the same. Here, for different policies, the variance or the effective sample size can be very different depending on how far this policy is away from the logging policy. So it's very easy to overfit if you go far away because your effective training set size, it becomes so small. So you need to constrain where in your policy space you're searching to get reliable results. And so there's, you can actually do learning theory about this. And so here again, in terms of minimizing a loss, not maximizing a reward, what these learning theoretical bounds tell you is that the true error is upper bounded by my training error plus a capacity control, that's like in regular supervised learning, But also, you need to take into account the variance of your estimator for that particular policy. And that's something that you need to optimize over as well. So, learning theory, you always have to take with a grain of salt. These bounds are never particularly accurate. They're always loose. But they always tell you something interesting about how you should design your learning algorithms. And basically what this bound tells you is that what an algorithm should optimize is something like that. It should optimize the training error, here IPS estimator, for example, with some regularization constant that you need to tune, the variance of the IPS estimator for any particular policy that you're currently evaluating, plus a capacity control to get consistent learning. And there have another, that's the regular kind of L2 normalizer, regularizer, or something like that. So the learning theory tells you, gives you a design principle for how to design algorithms for this off-policy learning that have these three components. And we call this counterfactual risk minimization in the kind of analogy to structural risk minimization, where you just have this one regularization term. Here you have two regularization terms based on the variance. So how do you turn this now into a learning algorithm? Well, you have to pick a class of policies that you want to optimize over. And by far the simplest and also the most popular way is to just use stochastic softmax policies. Like softmax, you know, from the output layer of a deep network, right? Or actually, this is exactly like a conditional random field as well, where you just have a kind of a joint feature map between the context and the action. That gives you a feature vector, phi. And then you, here in the simple case, we just learn linear parameterization, like a weight vector W. And then this function z, this partition function, just normalizes this whole thing so it becomes a probability distribution over actions. So again, this is like a conditional random field, you know, we know a lot about how these softmax policies work. So then really what you just need to do is you need to take this policy space and plug it into this counterfactual risk minimization objective. And this looks a little wild, but it's really just taking what we had before and then putting in the policies, this kind of these softmax policies. And you get an objective that this is the IPS estimate of the training error. This is the variance of the IPS estimator. And here we have an L2 regularizer to keep the capacity of the system under control. And then, well, it's not obvious here, but the whole thing is differentiable, and you can do gradient descent on it. And with some tricks, you can also do stochastic gradient descent on it. So again, you can use IPS or doubly robust as your training error, so to speak, here. For regularization, there's a key difference now. You have a standard regularizer, but also you need to regularize the variance, right? Because different policies in your policy space can have different variance. You don't want to go way out there where you basically have no data. Stochastic policies are nice because stochastic policies are differentiable, and that's why you can do gradient descent on this thing. You couldn't do this for, if you had deterministic policies, or you would have to have some surrogate loss. And then, you know, do gradient descent. So this is a different set of problems here. These are actually multi-label problems. These are actually combinatorial output spaces, but it's not that important. So this compares just regular IPS with normal kind of regularizing the weight vector and this what we call POEM. That's the name for this method, where we regularize also the variance. So the logging policy starts out with this performance here. And these are 4 different data sets. Lower is better. If you do IPS, just regular IPS optimization, here it actually, it improves actually on all tasks sometimes. But if you do the variance regularization in addition and really kind of make sure that you're not kind of going off into spaces of the policy space where you don't have any data, you gain quite a bit of performance, right? Again, lower is better. So that's one of the important things that's kind of different from supervised learning. We have to regularize based on variance, or that typically helps. The second thing is there's actually yet another way of how we can overfit. And there is a new, again, it's something that you don't have in supervised learning, and it's called propensity overfitting. And let me explain what that is. So here's an example where we have, again, different kind of customers in this direction and different actions that we can pick in that direction. That's our log data. Green means good, red means bad rewards, and the blue boxes mean that is the choice of the logging policy. So these are the rewards that we observe in our training data. The other rewards we don't observe. Now, let's minimize our training error here in terms of the IPS estimator. And what will the IPS estimator actually do? How does it minimize? Or what's a policy that actually minimizes the rewards, the losses? And actually, just avoiding all of the training data, avoiding all of the observations is like, in terms of the IPS estimate, it's the perfect thing to do, right? That gives you a loss of 0, an estimated loss of 0. So here, for example, these are the choices. This is a policy that minimizes the IPS training error. And the more I avoid actually the choices of the logging policy, the closer I get to 0, which is clearly not what we want. So the problem is that we have two random variables here, right? Normally, in supervised learning, we have one random variable, which is the reward. And we can overfit to kind of the randomness in that random variable, in the reward. We now have a second random variable, which is the choice of the logging the policy and the propensity. And that's another thing that we can overfit to. And overfitting to the choices of the logging policy, that's what's called propensity overfitting. So we have two types of overfitting to deal with. Fortunately, the propensity overfitting one, this new one, is actually pretty easy to deal with. And here's the trick, and it goes back to the SnipIPS estimator. This is just the IPS estimator, right? And this is the IPS estimator where we replaced the rewards, the actual rewards, with 1. So basically what this is just a fancy way of estimating the number 1. And we know that the result has to be 1. And if it is not 1, then we should become suspicious, right? In particular, if there's control variate, that's what we call this S here, if it's different from 1, that's a sign that some propensity overfitting must have occurred. And now look at it. If this here is a value that's much larger than 1, that probably also means that this is larger than 1. Because they basically share the lots of the formula. They're highly correlated. And if this is less than 1, then this is probably also going to be kind of too low. And the nice thing about the SnipIPS estimator is it takes the ratio of these two things. And so it corrects in this multivariate control variate fashion the IPS estimator for propensity overfitting. And so, if this is too low, it will divide by something and kind of upweight that. That's also part of the intuition why SNPs work so well. And it also helps with this propensity overfitting. So what does it mean? Well, we shouldn't actually be doing this counterfactual risk minimization with the IPS estimator, but we should be doing it with the SNPs estimator. But so we just measure training error by SNPs, We use the variance of the SNIPS estimator here for variance control, but the rest is basically the same. We call the SNIPS poem or norm poem, where it's just changing the estimator. The kind of nasty part becomes it's kind of more difficult to optimize because you have ratios here. And you could still do gradient descent on it, but it gets a little hairier. But you can still do that. And here are the results. Same data sets as before, both now using, I think it was an LBFGS, or maybe just a regular gradient descent, not stochastic gradient descent. And what you can see is if you control for propensity overfitting by using SNIPS, you get another nice boost in accuracy. And you can also look at these control variates. Like for the policy that the regular poem, the IPS poem finds, this control variate can be way off 1, which is a bad sign, right? It should actually be 1, but it's like overfit the propensities. If you do the same with SNIPS, it's much closer to 1. Which kind of indication that this actually works. The question then is, okay, can we also do this with other, not just with the conditional random fields and linear models, but can we do it with deep networks? And the answer is, conceptually, it's very straightforward. Most deep networks already have a softmax layer as an output, and so we can just use a softmax neural net. It's differentiable. We can do, we can just plug that in and do exactly the same thing. So again, same principle. We want to use SNIPS, the variance of SNIPS. The difficult part is how to optimize this thing. And for deep networks, we really want to use stochastic gradient descent. But you can actually reformulate this problem here equivalently into a sequence of optimization problems that gives you the same solution as the SNIPS solution. And then you can use stochastic gradient descent. So you can do that as well. Now, I'm not going to go into the details there. All right. So these are the 2 key things, I think, to keep into account when you're doing this off-policy, model-free policy learning. And then very briefly, I still want to talk about this special case of learning to rank, because it's actually very similar as well. So when you're doing learning to rank, there is, typically you have click data that looks like this. You have presented a particular ranking here, and then you've seen the user clicked on this and clicked on that, right? So you have a production, you have queries coming in, these are a P of X. You have a deployed ranker that gives you rankings. That's pi null, and you want to learn a new ranker that hopefully does better than pi null. So why is that similar to all of these contextual bandit problems that we had? And even going beyond what Yuta said before, where we actually explicitly randomize positions. Here we'll not randomize. Our logging policy is not going to be stochastic, but we'll exploit the randomness in our user behavior. The randomness in user behavior in this case is actually great. They do the exploration for us. So let's say this is the ranking that we presented, and this is the ranking that we want to evaluate, simplest case. If we knew all the relevance labels, it would be easy to compute DCG, or something like that. And for the simplicity of this talk, I'll just use as my quality metric the rank of the relevant documents. So lower is better here. So 3 plus that's 9, that's 16, right, is the kind of average, the sum of the ranks of the relevant documents here. Here it's 7, this ranking is better, easy, right? But if we have click data, this is what our data looks like. We've seen a click on the 3rd position. That maybe tells us that 1 and 2 were not relevant, but we don't know what's happening down here, right? We just don't know. It's unobserved. It's counterfactual, right? What would have happened if the user had gone further down? And so if we now have a new ranking, then, and these get kind of dredged to the top, how do we deal with the lack of information here? And the answer is that we can again use inverse probability or inverse propensity weighting, these IPS estimators, to deal with that as well. So we have our, our metric here. It's the rank of the relevant documents. And we'll use a very simple click model here. And the click model says, if we see a click, then that means the user has observed that document, seen it in the ranking, and it was relevant. And vice versa. If it's relevant, the user sees it, the user will click on it. That's it's a simple, somewhat realistic click model. But what does a no-click mean? No-click is ambiguous, right? If you don't see a click, it could be either that the user didn't see it or that the user didn't find it relevant, and we don't know which one it is, right? We need to kind of tease these two apart. And deterministically, we can't tease them apart. We can't look into the user's head. But stochastically, we can, using the same tricks of IPS weighting as before. So in particular, if we know the probability with which a user looks at any of these results, then we can just up and down weight the observations using the same IPS weighting tricks that we've done before. So let this Q of O, the probability of observation, that's in this column here for my mocked up example. And what does the kind of inverse propensity square estimator say here? If we see this only half of the time, if only half of the probability that the user goes here is only a half, every time we see a click on this result, we should update it by a factor of 2. And down here, if we see it only 1/5 of the time, every time we do see a click, we should upweight it by a factor of 5, right? And then in expectation, we got the right reward. So what we get is, average rank or DCG, just like Yuta said before. We can estimate this and get unbiased estimates subject to the fact that these observation propensities are correct. So now we can do, again, empirical risk minimization with that, right? We have an unbiased estimate of the loss of each ranking. It's not deterministically correct, but in expectation it's right. If we have now many observations, we average over those. And so what we get is we get a consistent estimate of the true ranking performance, let's say true DCG of our metric. And now we can optimize that with a learning to rank algorithm, and we get a consistent learning process under standard assumptions. Two questions that we have is how do we actually solve this argmax or argmin here, right, in a practical algorithm? Is that feasible? And the second one is how do we get these observation probabilities, these propensities here, right? So the first one first. That's actually pretty easy. How to solve this optimization problem is here, this is just for one algorithm. This is a ranking SVM. If you know a ranking SVM, you will realize that the only difference in this whole thing is that there is a factor 1 over the probability, 1 over Q in here. The rest is exactly the same. And so there's just a little bit of weighting, an additional constant in here. So we already know how to do this. All the theory about these learning to rank algorithms, these pairwise learning to rank algorithms, carries through. You can do this for other methods as well. Like if you want to have a deep network as your ranker, you can do that as well. So actually, it doesn't change. Nothing really changes. It's actually very simple. The second thing, that's the more tricky one, is we need to come up with these observation propensities. How likely is it that that the user is actually going to see this result? And there's a lot of modeling involved there. And the better our model there, the better the results. The simplest one is the position-based model, where we simply say that the probability of getting a click depends on the relevance of the result and the rank of that result. And so that means that the probability of the click is just the probability that the user goes to this rank times whether it's relevant or not. And so that is a simplifying model. Basically, it it doesn't take any dependencies into account. It's a little bit like the independent model that Yuta had in the beginning, but here we're not doing any explorations. We're just using the fact that users are random in how far they go down, and that's the randomness that we exploit. How do you estimate these? There's actually interesting little tricks that you can do. You don't need to strap people into eye trackers or anything like that. You can do little swaps in here as interventions, controlling for relevance that way, and you can estimate these Qs remotely with arbitrary accuracy, conditioned on your model. So, and if you kind of do this, you get the typical types of kind of learning results. This is the number of training examples, so the number of clicks. And now this is the performance. Lower is better. The dashed black line is the performance of the policy that collected the data. It was pretty bad. This line here is the best performance that we can hope. This is like, this is simulated data, so we know if we trained a regular learning to rank algorithm, it doesn't use clicks, but has the full relevance judgments available. This is how good you can get. And this red line is, if you do this bias, this inverse propensity learning to rank, eventually you get a consistent learning process, and you converge to the performance of what you would have gotten if you had actually had all the relevance judgments. The green one is if you use a biased learner that doesn't correct for the position bias, and that is biased and levels off and doesn't improve anymore. All right, so I talked in detail about pairwise learning to rank. Listwise learning to rank, I want to skip. People who know listwise learning were probably wondering, oh yeah, can you do this as well? Yes, you can, and I'll just refer you to this, this paper for doing that. All right, with that, I want to hand over to Yuta again. And we need to switch slide decks. Thank you.
Perfect, thanks. Okay, thank you, Thorsten. So this is gonna be the very end, the final topic of the main tutorial. So let's talk about how to implement. So we've done lots of stuff. I mean, the policy learning stuff and policy evaluations and lots of estimators. So let's now implement it in our research papers or in practice, of course. So topic of this final section, there are roughly 3 parts. So let me now formally introduce the package, the OffPolicy pipeline. What is it, or how can we use it? And next, I'm gonna introduce how this OffPolicy, the OffPolicy pipeline can accelerate our research process. How can we do policy evaluation or policy learning experiments when you try to write a research papers? And right after that, I'm gonna briefly introduce how to implement policy evaluation offline learning in practice using a real-world funded data. So let me just, again, formally introduce the package. So OffPolicy pipeline, this is a Python package for OffPolicy evaluation and learning. And yeah, please check out the GitHub repository. This is, I think, a nice repository. And also, welcome your studies and folks, welcome your supports. Of course, if you find it interesting or useful. And there are mainly 4 main modules, that set, policy, simulator, and of course, OffPolicy evaluation module. I think that's the main module. And by combining these modules, we can, simply construct a standard OffPolicy learning and OffPolicy evaluation flow. We first input bandit data. We can handle synthetic data, classification data, and also real-world bandit data with the OffPolicy pipeline, which is good. And then we run some policies, new policies, aiming for maximizing the policy values, the policy performance, the policy, performance of decision-making policy. So we train a new policy using only log data, that's OffPolicy learning, in the previous section. Right after that, we want to evaluate the performance of the newly trained policy, again, using only the validation log data, that's the policy evaluation. That's my part in the first section. And if you are a researcher, you may want to evaluate and compare the performance of different off-policy estimators, right? We want to know what estimator is going to be the most accurate estimator among some candidate estimators. That's going to be the evaluation of off-policy evaluation. It is like very relevant to the research process. We can do all the stuff very easily with the open-banded pipeline package. So again, research of open-banded pipeline contains functions to facilitate or accelerate our experiments in off-policy evaluation, or maybe your own study. You can just enjoy your, play with the synthetic data, and you can see how estimators work empirically. So researchers can implement their own, off-policy evaluation methods. They should, propose a new off-policy estimators, and then they can compare their new off-policy evaluation method with existing estimators very quickly, in a reproducible and standardized manner, because open-banded pipeline has already implemented a wide variety of existing off-policy estimators. You don't have to implement the baseline estimators anymore. And practice, it is also useful in practice, I think. It contains functions to implement real-world applications, of off-policy evaluation and learning. And actually, the real-world implementation part in my RecSys work utilizes this open-banded pipeline to productionize off-policy evaluation in the company I collaborate with while we was in Japan. And also, I think it also helps students and newcomers to the field to get to know the area. So in detail, we have some main modules. So that said, there are 3 main functions, there are 3 main Python classes. So real-world banded data, we can handle real-world public banded data, or you can just define the real-world banded data set class to load or pre-process your own company data. That's also possible. Synthetic banded data, I myself use the synthetic banded data set class heavily in creating this tutorial content in the first half of course. I use a many variety of synthetic data, and it's very flexible. And also much class banded reduction. So I think it's usual for off-policy evaluation researchers to use classification data in their off-policy evaluation experiments. There's a nice trick to transform classification data to a real banded data. But I think the process of transforming classification data to banded data is a little bit complicated steps. And also researchers implement the experimental procedure independently by themselves. So the implementation available are not so the standardized. But now we have a multi-class banded reduction function here, and it extremely simplifies the experimental process using transformed classification data in off-policy evaluation experiment. I think it's cool. And there's also a policy module. Contains IPW, and IPW is exactly the same as IPS. IPS, IPW, there are lots of names, representing exactly the same concept. IPW just maximizes the IPS objective from log-banded feedback data. We can do that policy learning very easily by using this function. And there's only neural network policy learner, so we can also model or represent the policy by using neural network architecture by using this class. There are also actually online contextual value algorithm implemented in this package, but of course, including the UCV, Thorsten sampling, Epsilon greedy. But our main focus is the offline side or batch learning or evaluation side. The main package and the main module is off-policy evaluation, of course. We cover the literally a wide range of existing estimators, including the direct method, IPS, self-normalized ones, W-robust, of course. The shrinkage estimator, there's also a nice recent estimator named more robust W-robust. And also we support the hyperparameter, automatic hyperparameter tuning for all the off-policy estimators having hyperparameters. So you don't have to handcraft the hyperparameter anymore. You can just data-drivenly search a good hyperparameter for off-policy evaluations if you use this package, which is cool. And also there are some advanced packaging, advanced settings. For example, there are some basic estimators for the continuous action setting, which is relevant to maybe the pricing optimization problem. We can do that. And also the combinatorial action setting. This is a very recent field, but we implemented all the basic estimators for the combinatorial action setting, including the vanilla IPS, and independent IPS, and reward interaction IPS, all included in my first half talk. So you can, just implement these kind of recent advances with this package. So you can just easily install the OffPolicy pipeline with a pip install, of course. The newest version is 0.5.1. It's frequently updated, so please make sure that you have the newest version. And so there are many example scripts and notebooks, tutorial notebooks available on the GitHub repository. So if you're interested, please look at these tutorial example scripts or notebooks. Maybe they are very useful to run what's going on in this package. So this is just an introduction. So let's look at how it works, how it can accelerate our research process. So this is kind of a research-motivated part. So you are now a researcher, and you want to write a paper about like OffPolicy learning or OffPolicy evaluation. So of course, you have to do some experiments in the last part of the paper, right? So the topic here is how to implement that kind of OffPolicy learning or OffPolicy evaluation experiments using synthetic data. So in OffPolicy learning experiment, you as a researcher, of course, you try to propose a new policy learning method that possibly lead to a better policy value than some existing methods, right? This is a very basic motivation for policy learning experiment, I think. And in policy learning experiment, of course, a policy measure, performance measure is going to be the policy value. And we somehow have to evaluate or estimate or approximate this policy value of the proposed method, your proposed method, and some baseline policy learning method, and then you have to compare. And then hopefully the proposed method has going to be it's going to be the highest policy value method, right? That's the policy learning experiment. So how about the policy evaluation experiment? So then you want to propose a OffPolicy evaluation estimator that possibly lead to a more accurate or lower mean-scale error estimator than existing estimators, including direct method, IPS, or WROS. We want to improve those existing estimators we learned in the first half of the tutorial. And again, the performance measure of the OffPolicy estimator is going to be the mean scale error. So again, this is defined as the expected square distance between the true policy value and the OffPolicy estimate or the estimation result of policy evaluation. And we can know the true policy value because we are now using synthetic data, right? So you have to evaluate this MSE of the proposed estimator and baseline, some baseline estimators, including IPS or WROS or maybe the shrinkage estimator, and then you have to compare, and that's it for the policy evaluation experiment. And this is kind of a very broad, rough possible experimental flow for policy learning experiment or policy evaluation experiment. So of course we have to generate synthetic data first. And then we train some bounded batch offline bounded policies in the second step. This is going to be your proposed method when you do a policy learning experiment. If you do a policy evaluation experiment, the second step is going to be your the arbitrary policies depending on your purpose of your experiment, right? And the third step is going to be the estimate of the policy value. We can somehow very accurately estimate or approximate the true policy value because we know that the data generating distribution when we use the synthetic data. So we can just use this policy value to compare the different policy learning methods, right? So that's it for the policy learning experiment. So policy evaluation experiment is a little bit more difficult or a bit complicated than the policy learning experiment because we have to do one additional step, which is just a policy evaluation of the trained bounded policies, and then we should be able to evaluate the performance. Performance, I mean the accuracy of policy evaluation. And then we compare what's going to be the most accurate of policy estimators among baselines and your proposed estimator, right? That's going to be the broad, rough view of the policy learning and policy evaluation experiment, right? So let's look at how we can implement those kind of experimental research papers or your own study with OffPolicy pipeline, the package. So the first step is going to be the synthetic data generation. And we prepare the synthetic bounded dataset class in the dataset module of the package, right? And this is a very flexible and also easy to use. What we have to do is just to set the number of action of the log data. Of course, if you are interested, you can just set a very large number to this number of action. And also, we set the number of dimension, and we can define the reward function. This is the expected reward function. There are some default, like pre-implemented reward function. And also, you can define the more complex reward function if we want to do the experiment in that nonlinear reward environment. And after that, after defining the synthetic bandit data set, what we have to do is just to call the function, the obtain batch bandit field function with the number of samples. And then we can just have some IID samples from the joint distribution defined by the login policy. Okay? So I now just sample the training bandit data and test bandit data independently in the last part. This is the inside of the training bandit data. This is just a Python dictionary. We have a context. This is a NumPy matrix, of course. And we see an action here. Now we are generating the discrete actions. And also we see a reward. So this is now a binary reward. And the final part is the expected reward. This is a R function. And this is actually a NumPy matrix because we have to have an expected reward for every different discrete action, for every different context. So this is going to be the matrix. Okay? We can notice expected reward because we are now using synthetic data. And the next step is going to be the training bandit policies or off-policy learning. So there are some off-policy learning methods implemented in the package. But I think the first choice is going to be the IPW runner, which is implemented in, of course, a policy module of the package. Again, IPS and IPW is just exactly the same as the IPS. There are some different names. And just the package is using the IPW. But what this policy learning method is doing is just to maximize the policy value estimate estimated by the IPS estimator, right? So we can do this maximization or policy learning process by using only the observable available log-bandit field data. So this is not so trivial to implement from scratch, but now you can do it very simply because we have this package. So now this is the IPW runner, and what you have to do is to just choose your favorite scikit-learn classifier, right? So I'm now using the logistic regression. This is, I think, the fastest, very easy to use function, but you can also use your favorite ones such as a random forest, support vector machines, or gradient boosting. And right after defining the IPW runner, the policy runner, and then what we have to do is just to fit and predict the new decision, and then we can make the new decision making, right? So we can call the fit function, and then we can learn the policy parameters, and right after that, we can just make a new decision making for the test data, right? So here I'm using the training bandit data, and the next step is going to be the test data, of course, because we have to make new decision making for the test data by using the training data. So this is almost the same as the supervised machine learning. We can also use a neural network policy learner, which is a different function implemented in the same module. And so I use the logistic regression, the more simpler method in this part. But if you want to be more complex, or if you want to be more advanced, you can use a neural network to model the policy parameter or the policy class. And then also you can use the more advanced objective, the W-bus objective. And then you can just maximize the W-bus objective to train the policy parameters from the log data. And also Thorsten mentioned that there is a variance regularization technique. And also you can do that by just activating the variance regularization by set the positive hyperparameter, now 0.1 to the variance regularization parameter, which is pretty simple to use. And also we can set the batch size or some other standard hyperparameters, of course. And after defining the class, exactly the same. By calling the fit function, we can train the policy parameter of the neural network policy. And after that, we can make a new decision making for the test data by the trained neural network policy with W-bus objective, which is cool, right? So this is going to be the output of the policies or the decision making. This is also going to be the NumPy matrix because we have a probability distribution of actions for each different context. So this is a deterministic policy example. But we can also have a stochastic type. And stochastic policy output is going to be this form, right? So every row of the metric is a distribution of action for each given context. I think it's pretty easy to interpret, okay? And now we train some policies. Right after that, what we have to do is to very accurately approximate the ground truth policy value of the trained policies. We can do this because we now know the expected reward function, or we know the data generating distribution of the synthetic data, right? And also, we can simplify this process by using the package. The package already supports the calculate ground truth policy value function. And then you can have the very accurate approximation of the trained policy. Now, the IPW, so we trained the IPW runner, and the performance is 0.7544, blah, blah, blah. And I calculated also the login policy performance. It was 0.59994 for this particular synthetic data, meaning that the package is working, right? We improve upon the performance of the login policy here, meaning that the IPW runner seems to be correctly implemented in the package. And we can just use this value, the policy value, to compare several different policy learning methods, possibly including your proposed method. So this is a policy learning experiment using synthetic data. But if we want to do some experiment or comparison of policy evaluation, we also have to do some additional steps. And the next step is going to be obtaining a reward predictor or reward estimator, right? The R-hat function or the reward estimator are used in direct method, W-bars or shrinkage estimator, or model-based estimators. So if you use this kind of model-based estimators in your baseline estimators or baseline of policy evaluation methods, you have to first of all train this R-hat function. This is not so trivial because we have to predict or we have to estimate the expected reward for each, every different action, right? So I think this is not so trivial to implement from scratch, but you can also simplify the process of obtaining this reward function by using the regression model class. This is implemented in the policy evaluation module of the package. And then what you have to do is to combine this regression model class with again, your favorite choice of a scikit-learn classifier or regressor, depending on the reward type. Here we are using the binary reward, so this is going to be the scikit-learn classifier. Now I'm again using the simplest one, the heuristic regression. And then what you have to do now is just to call the fit predict function. And then you're going to have the estimated reward for the test data or the validation data. Right? This is also going to be the NumPy matrix. Again, because we have to estimate the expected reward for every action for every context. Okay? I think it's pretty simple. What you have to do is just to choose the basic predictor or the machine learning method. And after that, we can do the policy evaluation itself. So there is another great function, which is a policy evaluation function. This also extremely simplifies our process of doing a policy evaluation with real-world data or in practice. So what we have to do is to define this function of policy evaluation here, and we just give the data that is going to be used in policy evaluation. Here, the test data or the validation data, maybe. And also, we have to, we're going to give the estimators that we want to use. And of course, IPS, direct method, W-bars are all implemented in the same module. So we can just import the estimators, and then we we give the IPS, the direct method, or some other estimators, the policy evaluation class, and then it's almost done. What you have to do is just to call estimate policy values function that is implemented in the policy evaluation function. And then you're going to have the policy evaluation result for each given policy estimators for the evaluation policy, all right? So the true policy value, here, this is just the previous slide. The true policy value was 0.7544, blah, blah, blah. And now the bottom one is the policy evaluation result I got in this synthetic data. And IPS and W-bars are doing great. I think they are pretty similar to the true policy value. So their prediction, their estimation was like the 0.751 and the 0.751. Only the direct method fails drastically, right? It drastically underestimates the true policy value in this particular example. But the important point here is that you don't have to implement the direct method IPS W-burst. They're already implemented, and what you have to do is just to pick your favorite estimators and done, right? And yeah, you can also implement the hyperparameter tuning procedure here. So there is a recent update in the package, and we implement this W-burst with shrinkage tuning, very state-of-the-art recent method. And you can do this. You can do with this package is like you just have to give some candidate hyperparameter values for the shrinkage estimator, right? The lambda hyperparameter values, and then this function automatically picks the best hyperparameter based on the hyperparameter tuning procedure I introduced in the first half, and then it automatically uses the best hyperparameter, and you can just do the policy variation with the best hyperparameter. You don't have to implement anymore. You don't have to implement the hyperparameter tuning procedure from scratch. Okay, then the final part is going to be the evaluation of a policy variation. So now assuming you are a researcher, so you maybe compare the performance of your proposed policy validation method and some baseline of policy validation methods. And the performance measure of the policy validation is going to be squared error or mean squared error. And we can also calculate this squared error by just using the evaluate performance of estimators function. And then we're going to have the squared error of the each estimators that we gave to the policy validation class. And in this particular trial, the W-burst is going to be the most accurate estimator. So evaluation of policy validation means that we can, we want to compare the estimation accuracy or the error in policy validation of several different policy estimators. Of course, this is just a single trial with a single random seed. So in the real research or in your study, you may want to generate the several different synthetic data with a random seed, with different random seeds, and after that you just take the empirical average of this squared error. Then you're gonna have the mean squared error of each estimators, and then it's pretty easy to compare. What you know that what's gonna be the most accurate estimator in the synthetic data. Okay. So that's gonna be the whole policy learning experiment and policy validation experiment with the package. I think it is much easier to use the package to implement these policy validation or policy learning experiments compared to implement all the stuff from scratch. You may have different impression, but that's my opinion. Okay, the final part is rest of policy evaluation or policy learning implementation using real-world bandit data. But actually, we can do we can implement the policy evaluation and policy learning life cycle very easily, again, using the data. It's almost the same process with the synthetic data, right? So I'm now using the open bandit dataset. So I released this dataset with some collaborators last year. So we collect the data from the Town platform. This is a very famous, I think the largest fashion e-commerce platform in my country. I never use it. I just use the platform for the data collection purpose. But I think this is a very famous, popular for young Japanese women. There was a very famous former CEO. That's the reason. But the important point here is that we learn some bandit policies to make the top page recommendation interface, and we collect some context and action choice by the login policies and click indicators as rewards. And if you're interested, you can just go to this page. But the important point, what I want to do here is to use that open bandit data to see how policy learning and policy evaluation work with real-world bandit data, right? So unfortunately, I cannot use my personal computer here, so I cannot, I cannot do the live demonstration. But I just, make put all the pictures on the slide. So let me do the hypothetical live demonstration here. So this is going to be a very quick, brief demonstration of off-policy evaluation and off-policy learning lifecycle with the real-world bandit data. This is kind of a very small, so there are some types of data sets, chunks of data sets in this open-bandit data set, but I used a relatively small data set for just the demo purpose, so that every numbers are not so meaningful. The purpose here is just to see how the package works, or how can we implement off-policy learning or off-policy evaluation in practice. So there are essentially 3 parts. So the first, I just load and pre-process the open-bandit dataset. We can do this with the dataset module of the package. And the next step is going to be train. So I use the random bucket. So there are some random bucket, or the dataset collected by random policy, the uniform random policy is in the dataset. So I'm using the random bucket of the open-bandit dataset here. And the next step is going to be, of course, the policy learning part. So the motivation here, we want to train the random bucket of the log data of the open-bandit dataset to train some new policies, possibly improving the platform recommendation performance, right? So I will train, in the next slide, I will train 2 different policies based on the log data of the open-bandit dataset. And the aim here is to improve the recommendation performance of the system. Totally fine. And the final step, so of course I'm using some like sophisticated neural network-based, for example, policies here. So maybe our intuition is that we should be able to do better than by using the new policies rather than the login policy, because login policy is not a uniform random policy. But this is just our intuition, right? So we have to somehow quantify our hypothesis of the new policies should outperform the random policies, and we can use off-policy evaluation to verify our hypothesis here, right? So the third part is going to be the off-policy evaluation, and I will evaluate these trained new policies by using off-policy evaluation, and then we can compare the performance of these new policies compared to the uniform random login policy, and also we can pick the best policy among, between the 2 new trained policies, right? And the final question here is that which policy to choose the platform, right? And the first part is going to be the bandit data pre-processing. So we already implement the open-bandit dataset class in the dataset module. So it is very easy to load and pre-process the dataset. What we have to do is just to set what kind of dataset we use in the open-bandit dataset. So I'm just using the random bucket of the dataset. And right after that, what we have to do is exactly the same. What we have to do is just call the obtain batch bandit feedback function already implemented in the class. And then we have the dataset, the train and test dataset from the login policy, now the uniform random policy. So this is just the brief statistics of the dataset I'm using here. The number of actions is not so large, just 80 unique actions, but I think it is much larger than the usual synthetic off-policy learning or policy evaluation experiment in research papers. And the number of sample size, the number of sample, it's 1,037,000. So it is, of course, much smaller than the industrial scale application, but I think it is more realistic than the nearly synthetic off-policy evaluation learning papers. So the next step is training bandit policies. So we can do exactly the same from the previous synthetic example. So I'm now using the IPW runner again as one of the new policies. So IPW runner is just train the policy parameters by maximizing the IPS objective of the estimated with the training data. And then we should be able to maximize the policy value only from the log data. That's the concept. And again, we can just combine our favorite choice of classifier with the IPW runner. I'm now choosing the random forest classifier, which is a little bit more complicated than the logistic regression, right? And then the rest of the stuff is exactly the same, just fitting the policy learner to the training data of the open-bandit dataset, the real-world bandit dataset, and we're going to predict the make new decision making to the test data of the bandit dataset. So that's the one of the 2 policies, and one of the 2 new policies. And the other policy, I'm using the little bit more sophisticated, seemingly sophisticated stuff. which is a neural network policy learner. The objective is the same, the IPW as IPS. So we maximize the same objective, IPS objective, which is estimatable from training data, the logarithmic data. But the difference is that we now model the policy class, the policy parameter by using neural network, not the random forest. That's the difference. But we don't know which is better, which is going to be the better in that particular data, right? So we want to evaluate the performance later. So neural network policy learner, almost the same. So I'm now using the Andam optimizer. We can set some solvers. And we can use, of course, stochastic gradient descent or momentum. That's your choice. And of course, objective, we can, of course, choose IPS. And right after that, what we have to do is just to fit the policy parameter of the neural network architecture. And also, we can easily predict the new decision making for the test data based on this trained neural network policy architecture, right? And the final step is going to be the off-policy evaluation, right? We cannot do many A/B testing in the real world, so we want to evaluate the performance of the new trained policies fully offline before deploying these policies in the real field. And we can use the off-policy evaluation we learned in the first half of the tutorial. And the first step is going to be always maybe the reward prediction. And again, we can do this with a regression model function in the off-policy evaluation module. And I'm now using, again, the logistic regression to estimate the regression model. So you can maybe do better by using like the light GBM or gradient boosting random forest here. That's your choice. But I'm just using the simplest one. And I just, the fit predict, the regression model. And then I'm going to have the estimated rewards for that reward bandit data. And we can use this to do the model-based off-policy evaluation, including the W-Buster direct method. And the final step is going to be the off-policy evaluation. Again, let me emphasize that I think this is a very simple flow. We need just 2 cells of the Jupyter notebook to do off-policy evaluation and visualize the result of the off-policy evaluation. I'm going to show the off-policy evaluation result in the next slide. But what I'm doing here is, again, I import the off-policy evaluation class, and I set the validation or test valid data used in the off-policy evaluation. And I'm now using the SnipIPS estimator and also the W-Bust estimator. Of course, it's your choice. And that's it for setting up the off-policy evaluation. And finally, we can also do the visualization of the off-policy evaluation result with this off-policy evaluation function. And I'm now using the visualize off-policy estimates of multiple policies. This is very useful to compare different policy learning methods using off-policy evaluation result. And this is the result. So I'm now comparing the random baseline, which is a login policy, the IPW runner with random forest. This is kind of a middle moderate policy, maybe the sophisticated one, the neural network policy learner. And this is a relative policy value, relative estimated policy value. And the baseline is a random baseline. So the horizontal, the black line is the performance of the random policy. And we see that the red bar, the IPW one, just using a random forest, maybe in expectation outperform the baseline random policy. But the black bar is a 95% confidence interval estimated with the policy evaluation method. So the lower confidence band is now below the random baseline when we use the IPW runner with random forest. So it has the potential to improve the random baseline maybe, but I think it might be the dangerous choice. But let's look at the blue bar, and it is doing great. And it is, it's about, it improves the recommendation of the login policy, the random policy, by about 70% in expectation. Of course, we are now using a relatively small login data, the logarithmic data, so the confidence interval seems to be a very large. But the numbers are not so important here. I'm now showing this, the live demonstration or result to see how policy evaluation, how policy learning work in practice. Okay? And I also confirm, I also have that the W-Bust also shows a similar trend. This is the W-Bust estimation result, but we see that almost the same result. But the point here is that the SnipIPS estimator and the WDBOS estimator are two very different concept estimators. So we can be more confident in the result because we now get almost the same result with the model-free estimators and the model-based estimators. That's the point here. Okay, and also the demo code here. Those codes are all available on GitHub. So if you're interested, please check the GitHub again. So that is it for the main content of the tutorial. And yeah, we're gonna together summarize the whole content of the tutorial right now.
Yeah, so maybe just a brief recap, brief summary. What we really want to drive home is that a lot of these recommendation problems can be thought of as contextual bandit problems. Context comes in, policy selection action, and then you observe the reward. You have log data from this. And so what this allows you now, that's the vision. And we've seen this now actually in industry really actually coming to fruition and working, is that you use the data that you already have, the log data, DNOW, and then you can do almost supervised learning workflows, where you do everything, all the hyperparameter tuning, everything you do offline. You have different learning algorithms, like neural networks or boosted trees. You try these all out, get different policies as candidates, and then you can use off-policy evaluation to then pick among all of these different hyperparameters. And all of this happens using exactly the same metrics, the same online metrics that you've trying to optimize in your A/B test or downstream performance, right, when you're putting it online. So there's no gap between online and offline evaluation because you're actually using the same metrics to evaluate both. You're just estimating them different ways. So you can spend all of this, doing all of this offline, all of this hyperparameter tuning offline, but optimizing exactly what you want. And then you get a prediction, like what Yuta just showed, of how well is this new policy going to do. Based on that, you can make a launch decision. And if it's good enough, you'll launch, but you probably want to put it through an A/B test just to make sure that you don't have any bugs in your pipeline, and then you roll it out. So it's a different workflow from an online workflow, and also a different workflow from a conventional offline workflow, where you have to work with proxy measures of the online performance, and you're never sure whether the proxy measure actually is predictive of what you're going to see online. So we've introduced these two classes, the model-based and the model-free estimators, and lots of things in between that give you a more favorable bias variance trade-off.
So first of all, we've seen conventional force evaluation and learning in the beginning of the tutorial, but there are lots of implicit, always neglected assumptions. For example, the action. There's only single and discrete action in standard force evaluation. There was only a single login policy. And actually, I got a very interesting question during the coffee break about the multiple login policy stuff. And also, we have to handcraft hyperparameters without, when we don't use the hyperparameter tuning method. There's no distributional shift, and always a one-sided utility. And we always think about the simple contextual value setting, but there are lots of recent advances, great advances. And for example, I talked about the combinatorial action. It is still an ongoing problem. It's very challenging to apply a force evaluation to a combinatorial action setting. Of course, we all want to do that, but there's a huge research possibilities, I think. Continuous action, there's also a growing field. Multiple login policies, of course, hyperparameter tuning. I talk about the great baseline hyperparameter tuning method, automatic hyperparameter tuning. We now don't have to care about how to handcraft hyperparameter tuning. We can do that data-drivenly. And also, there are some papers recently, how to address distributional shift, multi-sided platform. This is also an interesting topic. And also, the offline reinforcement learning is another growing field, I think. And the last part, we cover how to implement a policy evaluation or policy learning experiment and in practice. And if you're interested, of course, please look at the repository again. And there's some remaining challenges in the field, of course. So let me also emphasize that the large action space, the combinatorial action space, is a really relevant problem setting to the RecSys community or the ranking or the information retrieval community. But it is actually a very, still a challenging problem. So yeah, you have to do some, extension or research around this topic. It's going to be very valuable, right? So there's a nice approach, combining the clinic modeling and voice evaluation, statistical voice evaluation. But this is just one possible approach. There might be some other much better approaches. So we have to extend that. Yeah, it's too challenging to deal with hundreds or millions of actions. Moreover, the benchmark data is also important for the research community. So I, myself, released one possible real-world public dataset, but it is not enough. We want to have more real-world data having different characteristics, and then we can identify what's going to be the bottlenecks, what's going to be the issue when we apply voice evaluation or offline evaluation in practice. Yeah, so more real-world benchmark data, which is going to be very valuable for the entire voice evaluation community. Hyperparameter tuning, it is also, I think, a very interesting statistical topic. There's only a few papers recently proposing automatic hyperparameter tuning from log-banded data or available information. And yeah, this is, in my, personal experiment in, playing with synthetic data, some of policy, hyperparameter tuning is very important to ensure the accurate voice evaluation. But when I talk with, collaborators, from industry, they always don't know, how should they tune hyperparameters from log data. So I think this is a very practically motivated research topic, but this is not that explored yet. So I think there's also a very huge research possibilities there, how to tune hyperparameters. And OffPolicy Estimator selection. This is another, a little bit difficult problem from the hyperparameter tuning for voice evaluation. The problem here is that, so we cover lots of OffPolicy estimators in the first half, from the direct method, IPS, SnipIPS, WWS, shrinkage estimators. Yeah, it's always good to have many choices, but we always don't know which estimator is the best for our application or our company data. I made a recommendation in the first half. I don't know if you remember it, but the recommendation was very simple. For the easy setting, let's use SnipIPS. And the challenging setting, let's use a shrinkage estimator with automatic hyperparameter tuning. You may think that you can use my recommendation, but actually it's very difficult. I didn't tell a lie, but the issue is that we cannot differentiate what's going to be the easy setting, what's going to be the challenging setting in practice, right? There are lots of factors to be considered defining the difficulty of voice evaluation. So we also, it's great to have a data-driven estimator selection program, right? So we want to data-drivenly identify the right estimator to use in your own practice. That's going to be another very practically relevant research topic that is totally unexplored right now.
So there may be two that I still want to point out is, we've talked about contextual bandits here, which is this one-shot decision-making. That's an approximation to many processes. How can we do this in a sequential way, right? Where we have, decisions that kind of accumulate some state, and where we want to kind of dependent on the state that, something in the state of the world changes, like the state in the user's mind, for example, changes. How do we model that? That gets us closer to full reinforcement learning, makes the problems more challenging, and, you get also the kind of complexity that comes with the state space from that. So we need to kind of be careful that we don't make it too complex, but also not too simple. And then finally, how do we actually design the logging policy pie now, right? We always have that we want to field a good policy that has good reward, but we also, at the same time, want to collect new data from which we can learn later again, right? And how do we trade this off optimally? There's an explore-exploit trade-off. That's different from the typical online algorithms that can kind of make a different decision at each step. How do we design these logging policies so that we kind of have a convergent process overall? So with that, I think we're done. I know that there are a bunch of questions online. We'll address them maybe asynchronously after this. We're also out of time here. If you have questions, we'll be here in the front. Come to us, ask any questions that you may have, and we're happy to stick around as long as it takes. All right. Thank you.
Thank you.